them. I think that's good enough. Let's jump to the next very important topic, finally. The optimal control. That's my favorite. Oh, this common filter is also my favorite. I have a lot of favorite. This is called LQR. That will be my, hopefully that will be the last lecture. Okay, how many classes I have now? 4? 3. Yeah, I think that's good enough to cover the, there's some lecture note here. Okay, so I think many of you have heard about linear quadratic regulation or linear quadratic regulator, which is called LQR. Okay, it's I would say a big milestone of or the basic building block of modern control theory. Okay, it's very important, but typically we don't cover this in the undergraduate class. But I think that's so important. I at least need to give you a short introduction to it. So won't be that deep, but at least you know what's going on and how to use it, so on and so forth. Okay, and it has been used a lot in the robotics, especially recent years. Okay, if you read a lot of any kind of papers talking about control of different robots, I think they all kind of involve LQR or its advanced version, like MPC. Okay, I think the kind of concept extends to model predictive control. So if I have time, I can give one lecture on model predictive control. You will see the connection between these two. Okay, and also to really understand LQR, again, it's similar to the Kalman filter. It's just a few lines of code, a few equations. The key is that how do you make sure you understand what's going on? So that's why when you see different variations, for example, like at the beginning of the last lecture, I told you that we doesn't need to assume linearity with respect to control, right? So if you know what's going on truly, you can easily do those extensions. But if you don't know, then you have to match the formulas, okay? So I have to teach you optimal control and dynamic programming to the level that's sufficient to cover linear quadratic regulator. And dynamic programming is my favorite. I have a lot of favorites. This is one of them, okay? And so I will make sure you understand this, all right? So today, let's get started with some kind of quick, short introduction. So far, I mean, our coverage so far involves pole placement or eigenvalue assignment to design feedback control laws. And then we talk about Kalman filtering. Okay, that's the two main things that we cover so far. Okay, when we design controllers, we care about what? As I mentioned before, you always think about your designing the control gain is trying to move the eigenvalues of your closed loop system because your eigenvalues determines your system behavior. Okay, but my first sentence is going to violate that assumption a little bit. So eigenvalue does not fully determine the transient. It is mostly for asymptotic. So whether the system is stable or not, and how fast it converges, roughly can be captured by eigenvalue, but it cannot fully determine that because there's other terms affect the convergence as well. But whether it converges or not, that's determined by eigenvalue. So it only determines the asymptotic behavior. Okay, you cannot arbitrarily kind of control the transient. And also, what's a good eigenvalues? What are good eigenvalues, you think? Based on our discussion before, somehow in discrete time, we need to have the eigenvalue in here, 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 inside unit circle. But somehow it's in there, you may not know what's the best eigenvalues. Which one is good? These 4. If you think the smaller the better, then I will just choose eigenvalue to be 0 or arbitrarily close to 0. Is that okay? Nobody do this, right? Then you have arbitrarily large control actions oftentimes. So we never formally see the word formally, right? We have a hand-waving way to discuss, okay, I cannot put eigenvalue too small because that will cause some bigger control or large control effort. But we never formally address this trade-off, okay? There's a trade-off, how fast you want the system to converge and how large you can suffer or you can tolerate your control magnitude. Those things can be done or can be formally addressed in the framework of optimal control, okay? So this is, you can think about this as metric-based controller design. So it's not only stable or not, you want somehow a criteria to tell you what are the best, okay? So the cost function, the metric, I think we can also call this optimization based, okay? You may not realize, okay, there are only 3 tools that we keep using throughout this semester, maybe in your entire life, if you stay in this major, okay? It's 3 things, right? I mean, the most important key thing that my favorite, right? Linear algebra, probability. The other one you may not realize is optimization, okay? If you view the topics we covered so far, least square, right? What we are trying to do to minimize the output with predicted output. So estimate some unknowns, and we're trying to minimize the deviation from our observation, from the model predicted output to the observation, okay? And for common filter that we just finished, filter, we are trying to optimize what? Minima, okay. X minus the best estimate. Given something, I optimize the best, the minimum, the mean squared error. That's what I want to minimize, right? All of this transform to optimization. Essentially, you're dealing with optimization either with deterministic models or probabilistic models. That's the key. This is the key, not only for this class, for modern, not control, modern engineering. What does engineering do?
Find a solution to real-world problem.
Find a solution to real-world problem, right? You may design your kind of robot, maybe mechanical design that doesn't need kind of optimization. But you should first ask, what is a good design? How do you quantify a design is good or bad? If you have that sense, and you can optimize it. All right? Whatever design, you're designing controller, you're designing mechanical parts, your motor, and your design have some parameters. You often want to optimize over these parameters according to certain cost criteria that before you may just in your mind, you think this will be good. Think about how you design, Yuntian, how you design a mechanical design. Cost functions in your mind, you have your own kind of prediction. If I make this, the thickness of this part, I mean, there's a lot of parameters you need to make decisions, right? And these decisions in your mind, you think, oh, that will lead to a good performance. I have some constraints. I need to make sure the force, right? You need to provide. You have somehow your own kind of cost function in your mind. You just didn't explicitly write that down. So what you're doing is optimization. Okay. So machine learning is also optimization. You know that, right? It's nothing but optimization. So match the data. So cost function, typically, how do we optimize over control laws? Okay, controllers. And cost function, we use cost function, right? We have to make sure we have a criteria to determine what is a good controller, what is a bad controller, and we can use cost function. Cost function can penalize your state deviation from your desired locations or positions, or penalize large control effort. That's also possible. So whatever you like, your desired behavior is, you can penalize deviation from that desired behavior. So now let's give some terminologies. Okay, the optimal control port that we're dealing with, I'm trying to introduce is very general, okay? We can do nonlinear dynamics. It could be like robots, whatever robot you feel like you want to study. And you have to be able to write this down as a dynamical system. This could be nonlinear, okay? And oftentimes, you may have state and control constraints. In other words, when you design your controller, you need to make sure your system satisfies some behavior, okay, or do not violate some kind of constraint. So I will give you an example. Suppose you are trying to design your motor controller. So for example, motor control. Suppose, okay? And this state constraint could be, say, my temperature is less than 80 degrees. I don't want to go over too high, all right? And the temperature typically is a function of your state. Okay, this is the T, is a function of your state, okay, x, k. At any given time, your state, somehow it should be a state of function. So state of function should be less than 80 degrees. That impose a constraint on the state. You want to design your controller to respect or to meet that constraint. And this one, so control also has constraint. For example, the torque, the maximum torque I can give is 35 Newton meter, for example. That would be, it's already pretty good, all right? 35 Newton meter, suppose. That will be your control constraint. That makes sense? For our previous design procedure, we didn't consider any constraint yet, but optimal control can allow you to do it. Okay, another term I want to somehow you get familiar with is control law. If you don't like the word law, you can think about that as controller. But what does controller mean? You have a controller. You always think about controller from diagram view. Controller in your function or in your system is nothing but a function. Take measurement or state and gives you what I think a good control action should be at this time. It's a mapping from state to control action, right? So controller or control law is a function of the state. And the value of the control law is the action you should take at this time, at this particular state. And for optimal control problem, you often need a so-called control horizon. And this is a discrete time, we'll say 0, 1, 2, 3, 4, 5, up to time n. This is the horizon n. If n go to infinity, then we will have 0 to infinity. This is called infinite horizon problem, okay? You consider all the future behaviors. You not only look at 10 steps. Okay, so infinite horizon problem. That's the terminology I want you to know. And there's a few things as well. That's control policy. That's when you do learning, is always reinforcement learning. That's also trying to solve. Reinforcement learning is trying to solve an optimal control problem. Well, if you want to talk to the CS students, then they're trying to solve a Markov decision problem, which is the optimal control problem for stochastic system, all right? That's roughly that. Policy, I would say pi. It's a sequence of control laws, let's say a sequence of functions, all right? And the control input sequence is a sequence, let's say U equal to U0, U1, UN minus 1, something like that. That's a sequence of numbers or vectors, control action. This is sequence of functions. For control law, for example, this guy could be mu1 x is a function of state, could be k1 times x, right? The gain times, is this a function? Yes, right? It's a linear function of the state. It's a linear control law. I can have nonlinear control law, right? This is only an example. I could have this, it's just a function of state. And policies can be viewed as a sequence of control laws. And that means your control law can change over time. Let's say if the control law doesn't change, so any given time, this block doesn't change over time. Your controller doesn't depend on time, then I can apply the same control law all the time. This is typically called stationary policy. I'm introducing more than what you need, but those terminology will help you to connect what I teach you to other kind of materials online or from other class. Okay, that's all terminologies. Any questions so far? It's abstract, right? You need to see examples. A term that I call a lot, I somehow refer to a lot, closed loop, right? I explain a lot as well. And in the controller design, we have closed loop. It's you plug in this control law, that's your controller, right? Controller determines control, and this is your system. Suppose we can measure all the state. The behavior of this closed loop behavior will be my closed loop dynamics, right? So if I have my open loop is like this. Open loop depends on what control actions I gave you. Control is undetermined yet. Undetermined. Okay? It's not determined, not specified yet. This is open loop. Okay, if I plug in my control law, right? If I consider this behavior, then the closed loop dynamics will be xk plus 1 equal to fxk mu of xk, right? You plug in your control. So your control already determined if your state is given. So this will be my closed loop dynamics. Okay, it only depends on state x. Okay, x only depends on state. The state keeps changing, so you have a closed loop dynamics. That's terminology. Some you may know before, some you don't. That's fine. Let's get more exercise. You will get familiar to most of them. And the key is that you want to make sure you want to quantify performance through cost function. Okay, don't argue if you don't have a criteria. I like PID, I like MPC, I like fuzzy control, I like neural network control, I like adaptive control, I like this method, I like that method. Those arguments doesn't make sense unless all of us agree upon a cost function. So what do you mean by good? You think this is better, right? This is good, but you have to specify what do you mean by good. Otherwise, it's just nonsense, right? You have to agree upon something. If your good is different from my kind of a performance, then metric, then of course, we will have different answers. If we agree upon a cost function or common performance index function, that means I just want the shortest path to that door. And if you think, okay, you think that's a good metric, so the shortest path to that door, then we can find our solution, and our solution should agree. All right? If you want to say, I want the shortest path, but the other one say I want the minimum energy. Well, that would be different. Okay. So the key is that for not only optimal control, for as I mentioned, modern engineering is to really kind of encode your objective, means what you want to do, to a cost function. And then you solve optimization problem. Okay, that's it. So let's see how we can quantify good performance or bad performance. For optimal control problem, so typically there's two kind of ways to define, to encode your objective through either so-called state cost, means running cost, or terminal cost. These two things. Okay, these are both functions of state, and the running cost also is a function of the control action. So we can penalize. So this cost is introduced to penalize. Cost means you want to make it small, right? So it used to penalize undesired behavior. Okay. Behavior. What do I mean by that? For example, if my desired penalize undesired behavior, you have to have some desired behavior first. Okay. Suppose my desired state, I want my state to stay close to, desired state is, let's say, x hat. Stay close to that x hat. Then and also small control effort, small energy. Then my cost function is a function of state and the control, could be x minus x hat squared plus u squared. That's one case, one possibility. Okay? What does this cost function do? Is somehow encode your objective. Okay, I want to stay close to that state, and I want to minimize my control effort. All right. If you want to say, I want to stay away from this as far as possible, this is some bomb location or dangerous location, then it will be different. You can use one overlay to encode that objective. So whatever objective you have to make sure you can write it down, quantify them as a cost function. Okay? Terminal state is just at the end of the game, you want to make sure you have the choice to specify, to penalize your deviation from your desired state. So this could be, for example, could be also deviation from this, maybe 3. Cost function is not given, right? It's whatever best explains your objective. It's your choice. Okay, there's no kind of a good choice for everything cost. And n-horizon cost function is, so you want to select your control sequence to minimize the cost, which is summation of the running cost plus the terminal cost. That's a standard formulation for optimal. If you minimize this, it will be standard formulation for optimal control problem. So now let's look at the general formulation. So our goal is, let's see, okay. So design, your controller can be viewed as select the best control action to minimize your cost function. This is a cost function, right? So it's summation of running cost plus G of terminal cost. That's the standard formulation. And I want to say all the control problem can be transformed into optimal control problem. Let me repeat. All the control problem can be transformed into optimal control problem, okay? Sometimes you may not have the time to write down your objective. If you have your objective, you can formulate it as an optimal control problem, but it's hard to solve. Okay, it's very hard to solve in general. Here I want to explain a little bit. This is so-called state-dependent constraint. So your control should be restricted. Before, the example I gave you is a torque should be less than 35 Newton meter. Any questions? What do I mean by state-dependent constraint? It's, for example, I have your robot should be moving. Those are obstacles. You want to from here to go here. All right, that's your goal. You want to find the path from the initial state to the final state. And at any given location, your control constraints are different. For example, I can tell you, suppose this is my A, then locally my control can move anywhere. Let me zoom in. Okay, I can move anywhere. But if I'm here, this is my B. The control action I can take is only allow me to move away from the obstacles. I cannot, there's some action is not allowed. For example, going here is not allowed. Okay, so if you specify your control action, the constraint you have is state dependent in general. It depends on where you are, the available control action you can take is different. Okay, if you have this, you want to minimize, you want to find the control sequence to minimize this cost function subject to those dynamic constraints and also control constraints. I want to also mention state constraint can be transformed to state-dependent control constraint. What do I mean by this? State constraint, for example, xk less than 2. That's my state constraint, right? Then that's imposed, that tells me, because I know my xk equals to xk minus 1, suppose, okay, plus 2 of uk minus 1. Suppose that's my model. That tells me, let's say, suppose, this is assume. These two things tells me that my uk minus 1 should be what? Less than 2 minus x divided by 2, xk, right? Sorry, x minus 1. Okay, so that's my, so this is a function of state. So your control constraints depend on the state now. So state constraint can be transformed into control constraint. Those are pretty abstract. Let's look at example. I think that's the best way to see how this works. Okay, suppose this is an aircraft example. This is a real kind of example, right? So this is how they design controller for aircraft early days. And this is the linearized model of the aircraft dynamics at a particular altitude, 5,000 meters, and at airspeed of 120 meters per second. And this is my state is, first state is angle of attack. Where is the angle of attack? This thing is angle of attack. And the second one is the pitch. And third one is the pitch rate. Fourth one is altitude. It's how high you're flying. Okay, those are for state. This is altitude minus 5,000. Okay, this is deviation from your desired altitude. It's not the true altitude, right? Given this dynamics, this is my A matrix. This is my B. This is continuous time. This is my C. That's a linearized model. Okay, our goal here is to stabilize it. To make x convert to 0. You want to make sure you fly with 0 angle attack, 0 pitch angle, and at this particular 5,000 meters, that means x4 also need to be 0. Okay, so our goal is try to make sure everything goes to 0. That's stabilization problem. But I have some constraints here, right? I have elevator angle cannot be bigger or equal. So elevator angle is the control, by the way. You know the elevator angle? And elevator range, that means the change of the angle cannot be too fast. And the pitch angle, that's a state constraint. I cannot have a too large pitch angle, otherwise I will crash. Right? You will lose your control. You specify this objective. Is this an optimal control problem? It's okay, so whatever problem is our superficially imposed things, right? It's our belief. As I mentioned, you can view all the control problem as optimal control problem. All, including this one, right? You don't have to. You can just say, I want to design a pole placement problem. Okay, that's fine. But you can always view this as optimal control problem. Let's see how we can do it. The DT model. Let's do discrete time, right? So I have A, B, C, D now. Do I have D? I don't, right? So then I can have xk plus 1 equal to A, xk, AD, xk plus BD, UK, and yk equal to CD, xk with discretization step 0.25 seconds. Okay, we can do it. I will show you similar examples maybe later. Okay? We can have discrete time model that we are studying discrete time model. We have been studying a discrete time model for the entire semester. Then we can choose cost function. What would be a good cost function for this example? There's two things, right? Running cost. There's no unique way to specify them. As long as they reflect what you want, then it's fine. Cost function would be xkuk. The running cost, I will see squared plus uk squared. Okay, I want the minimum effort, and I want the xk to be small as possible. Okay, this cost will be imposed or be accumulated over its time. Whenever you have a non-zero state, your cost will increase. Okay, you want to minimize it. Also, we can have a running cost, a terminal cost, which is g of xn. I can also say this is my squared. Okay, so maybe Xiaohan wants something else, right? Could be he wants this cost to be 100 sk squared plus uk squared. Is this okay? Whatever cost is okay, right? It really matters whether that reflects what you want. This cost differed from this cost. What's the difference?
The penalty is more.
Penalize more about state deviation, and you care less about your control energy. So you don't care about how much gas I waste, how much fuel I wasted. So it just I just care about my state deviation. So then you may, as a result, you may have a control trajectory that convert to zero faster, but may have a larger control effort. Okay, you can, by designing your cost, you're telling the system what you really want. Okay, and also you can choose constraint set. In this case, for example, the state constraint. Well, okay, let me write it down. UK, that's not state control constraint as well. UK is less than 0.26. And my second state, sk of 2, should be less than 0.65, right? What is it? is this guy. The pitch angle is the second state, right? So I will do this next time. Okay, let's take a break. Oh, I forgot the quiz again. All right, let's get started. It's the last lecture, which is lecture note 6. Not last lecture. I think it will be. Hopefully, it will be lecture 9. Today, we're going to finish lecture note 8. Hopefully. Okay, this lecture is about optimal control. So far, we have learned how to design what control based on pole placement. Okay, if we don't know the state, we can use observer. If the system dynamic has uncertainty, we should use common filter to observe the state. Once you have the state, you can do state feedback control, right? And based on pole placement, because that affects the closed loop dynamics. But last time we started talking about optimal control, and that's, I think it will be a unified view for almost all the control design problems. Some problem by nature is optimal control problem. Some of them may not look like a optimal control problem to start with, but you can think of them or reverse engineer them to become an optimal control problem. And so I think this, as I mentioned last time, almost all the control problems can be stated or formulated as an optimal control problem. Okay, and we start talking about the formulation. I think the key is that you should know your objective. So whatever your control design objective. I mean, whatever your objective is, it doesn't matter what it is, you should be able to convert that into a cost function. Okay? You want to stabilize it, you want to make it more stable, you want to make the transient less oscillatory, you want to reduce the percent overshoot, you want to track faster. All of these things should be able to convert it to a cost function. Once all of us agree on a cost function, then we can design a control to minimize the cost. In other words, to optimize the performance that you care. And that becomes, and how to do this, this is basically the topic for optimal control. We start talking about this last time, and we start talking about this example, I think, right? And as the first example, when you see engineering problem, I don't think they will have an optimal control problem statement for you unless you're in the exam, right? Or homework. I will tell you, okay, to solve this optimal control problem. In reality, you were given a problem described by plain English or Chinese, whatever. Okay? And you should be able to convert what you want to do into a kind of a cost function, right? This is the example we start talking about, right? Last time we talked about this is the model for an aircraft. This is kind of a real aircraft. And those parameters are, I would say, practical. It's not exact, but it's practical. Hold on. And this is a continuous time system, and we linearize it around certain operating point. Now here I want to emphasize that this state is deviation from desired state. Okay, so we want that to be 0. For example, when I say x1 is angle of attack, that means deviation from your desired angle of attack. That desired may be 0 or maybe not. I don't care. We only care about the difference or deviation from the desired. And altitude means a deviation from desired. Here is the linearization point. It's 5,000 meters. So that's the deviation from 5,000 meters. Okay, there's a pitch angle and pitch rate. Those are 4 states, and the only one input is the elevator angle. Okay, and that angle can be controlled but it also have some constraint. Elevator angle cannot be larger than certain degrees, and also the change, the rate to change it also should be less than certain speed. Okay, so that's the statement, and the system is unstable, open loop unstable, means that if you don't control the elevator angle, you crash. Right? It's like the mobile robot on the ground is stable, right? If you don't control it, stay there. But this system, if you don't control it, will fall, it will crash. So that's called open loop unstable. So our goal, I didn't say our goal, our objective, roughly speaking, is to regulate, right? To drive x to 0 with small energy. Let me not use energy. Energy is small control effort, loosely speaking. Okay, if I don't need to apply any control to achieve this goal, then that will be better. Okay, I want to use the minimum or smallest control effort to drive my state to desired. Okay, to 0 means to desired value. Okay, if you push away or have some disturbance, you deviate from your desired values, then you want to move back to it. Okay, so that's the goal. It's not an optimal control problem, right? But what we can define is we can formulate this problem as different ways. In particular, an optimal control formulation can be given as the follows, right? And since we're dealing with most of the time, it's the discrete time model, let's choose a discretization time step, which is 0.25 seconds. Okay, and now we need to choose cost function. As I mentioned last time, cost function have two parts. One is called terminal cost, right? The other one is called running cost. Running cost is the penalization each time. Okay, and terminal cost is only penalize the final state. Suppose you have a finite time horizon. Okay, in this case, the running cost is, I put it like a quadratic function, like a norm of the vector. Can we come up with other running cost? Yeah. Are you okay with it? I'm fine with any kind of running cost that loosely reflect my goal. Okay, but if you have a more concrete goal, so for example, you know the price of your gasoline, right? And you want to minimize the gas cost. That have a more concrete metric. 最小化你的油钱, okay. Okay, that's fine. That have a concrete number for the cost. For this case, we just say, okay, we want these two to be small. Each time you are non-zero, I penalize it. Okay, so the terminal cost here is also, we don't have a specific terminal goal. We want it to be 0, but if it's not 0, it's okay. If you deviate a little bit from 0, it's okay, but we want it to be as close to 0 as possible, right? So that's also put this one. You can put 100 or whatever that roughly reflect this goal. And then another important thing is that not only the cost, okay, you also have restrictions, constraints. You cannot do arbitrary things, right? So the constraint here is, first of all, the magnitude of the control action. The action is elevator angle. The angle cannot be larger or larger than this 0.22, 26. And also this is, what is this? The pitch angle cannot be too large. Any questions? If the pitch angle too large, then that somehow violates my assumption that maybe my linearization model will be invalid. Okay, so that's also should be considered. And what other constraints I have? For example, I have this one, right? Elevator rate. What does this mean? U dot, right? U dot. The change of U cannot be too fast. Otherwise, the lower level controller cannot accomplish this, right? So this is says this is less than 0.349. But this is it's a continuous time model. But what does this mean? I can formulate it as a UK minus 1 less than or equal to 0.349 times delta t. Is that okay? Let's roughly reflect what I want. It's constrained. It's constrained on the control. All right. So now we have our objective. If you purely have objective, that doesn't mean anything, right? You have to know your boundaries, what you can do. Okay, your control actions, that means the constraint. So overall, the optimal control problem is the following. So minimize summation of from k equal to 0 to n minus 1, L, xk, uk. That's the summation of running cost. Each time, you penalize deviation from your desired state, okay? And then I plus a terminal cost, which only penalize the last state, okay, at the final step. So, and the subject to, I need to consider constraints. First of all, the dynamical system constraint. X and k are not freely changeable. They are not free. You cannot arbitrarily pick xk and uk. They need to satisfy the dynamical system equations, which is, in this case, is linear, right? So k plus 1 equal to axk. I said it's AD, right? Discrete time. Did I say that? This is AD, BD, right? So this AD plus BD UK. This is my relation between xk, uk, and xk plus 1. That can be viewed as a constraint for the optimization problem. So these three variables need to satisfy this condition. Okay? And also I know uk has to be less than equal to 0.262, and the second coordinate of xk should be less than equal to 0.65, and also my uk minus 1 should be less than 394 delta t. Delta t here is what? 25, right? 0.25. So I can just write it down. Is this an optimization problem? Do you know what the optimization problem is? Minimize fx subject to x satisfy certain conditions. That's an optimization problem. This is an optimization problem, but it has a sequential nature. It has this dynamical system involved, so it also can be viewed as an optimal control problem. I want to ask you, what is the optimization variable? What do I mean by optimization variable? It's what you are trying to tune, to select. X and U? Only U, right? So U0, U1, all the way to UN minus 1. You have this number of U's. This is less, what is it? So you cannot see it. So this is 3 times 0.25, okay? Only you can see from here. All right, so those are the optimization variables. Once they are determined, then xk are determined. But you need to start from a x0, right? X0 need to be given. Suppose I call x0 a z, okay? So, so the solution of this, so this thing, it depends on z only. So this problem, of course, if I optimize over U, I've picked the best one, right? That's all my optimizer. And the whole problem somehow is parameterized by my initial state. If I change my initial state, this optimization problem changes. Okay? The optimal solution will also change accordingly. All right, that's enough. Let's look at another example that you may not view it as optimal control problem, but it's essentially it's a shortest path problem. Or when you're booking tickets, it's also airfare problem. So what's the optimal cost to go from Shenzhen to Guangzhou is too short. No. Shanghai, let's to the U.S. We cannot go there. And all right, so you need to take multiple. You need to take transit, right? Then you need to find out the best path, right? Okay, or you drive your car. What's your best kind of path from Shenzhen to Beijing, for example? That's somehow this kind of a routing problem or path planning problem, right? So suppose that we are given this figure, this graph, and I think this is the meaning is kind of apparent. So those are the cities. Okay, I want to visit. Suppose I start from A1. I want to get to A4. Here is A4. You cannot see it. I don't know how to move this, guys. Anyway, that's fine. So this is A4, and so it's the number. It means the length. Okay, between the two cities. Let's say that the length. Okay, so I want to find the best shortest path. And in your brain, when you do this, you will just enumerate all the possible paths, and you will find it. I think this is easy enough. You can do it by inspection, without writing things down. But let's consider a formal way to consider. Suppose you have a big, 1,000 by 1,000 cities network, right? So then it's hard for you to do it. Then you have to program, your computer to do it, and how to formalize it. There are different ways. There's a pure CS ways, computer scientist ways. And what I'm talking about here is not the most efficient, but it's a more general framework. Let's think about them as a state space dynamical system. Can you think that way? What's your state? Let's think about the state now. As I mentioned, there's no one tell you what are the state is. Okay, those are model, and all models are wrong sometimes, right? So it's really reflect what you want or not. There's different ways to view the same problem. In particular, this problem, we can view it different ways, but let's consider a state space approach, I think that's very general. The state space is all the cities. Suppose we have 8 cities, right? That's the state space. Previously, our X typically in Rn or in R, right? It's a continuous variable. But here, X can take values, 8 values. That's fine, right? Each value represents one city. You can think that way, right? And then I have a constraint set. I think this notation I explained last time. This is available control action you can take when you are at state X, right? And this thing can be, the constraint can be state dependent, as I have the figure last time, right? You remember? If you're here, your control action, suppose you can move different locations, different direction, versus you are here at the B location, your control action available for you, it's different. Here is the same thing. I would say this guy is a possible next site to visit. For example, I would say U of, let's say A7. What do you think it's? U of A7, it means, by definition, how many actions I can take at the U7, A7? 3, right? Suppose I can move back, I can go back to A1, I can go to A8, I can go to A6. So A1, A8, A6. That's my control action. Although it's discrete, it's still a set. My dynamical system in discrete time is nothing but state update equation. So given the current state, given the control action, you specify what the next state is. In this case, it's nonlinear, right? Of course, it's discrete even. So what is it? It's nothing but UK. So I can directly control my next state. It's a trivial dynamics. So each time you select where you want to go, but you can directly control where you can go. So this is nothing but this directly state the next set to visit, right? Next set to visit. Right? And then we can specify, depending on our objective, we can specify cost functions. If we want to minimize the total travel time or length, then the running cost is that if you go from, meaning running cost means what? It's a function of the state and function of the action you take at this state, all right? So I would say this can be viewed as the edge, in this case can be viewed as, defined as edge length. What do I mean by that is, for example, I would say L, A1, U can be A7, right? U is the next one I want to visit. X, A1, U equal to A7, let's say U equal to A7. Then this will be, the length, it will be 6. It's all notations, right? Any questions? A1, A7 equal to 6. I will say L, let's say A2, I can go A3, right? A3, that will be 3. It's this link. What about terminal cost in this case? Do I care where I finally is? Well, I can define either way. I can soft penalize, or I can do a little bit extreme in this case. I would say the infinity if Z is not my goal. If I want to go to Beijing, then I eventually go to Shanghai. That means my cost is infinity, right? I'm dead. So that's, if not A4, suppose our goal is to, suppose I need to specify our goal, okay? Start from A1, go to A4 with minimum cost or whatever the distance. Okay, so then if I'm already, the final state is A4, why I use Z? Z is a dummy variable. Okay, it's some function. Function is mapped input to output. Here I just use Z to denote a generic state. So if A4, then it's 0. So if I'm here, then I don't penalize you. Okay, so then the problem becomes, let's say, sort is path A1 to A4 problem. Can be formulated as the following: minimize L, summation, K from 0 to n minus 1, depending on how many times I want to give you, right? If I gave you one step, of course you cannot go there. Your cost is always infinity. So n is specified. It's time horizon. I allow you to solve this problem. And this is xk, uk, plus g of xn, subject to xk plus 1 equal to, in this case, is I have xk uk, and uk belong to capital U of xk. That's it.
Since the n is given, I think the control action we can take should include the state in the same city.
Yeah. No. Why?
Because
No, n can be 4 or 5 or 7. Yeah, it's given.
so if n maybe at n equals to 4, I have one of the shortest path, and n equals to 5, I can't.
Yeah, sure, yes, of course. If you're given more than, let's say, the minimum path is from, let's say, 2 steps, 1, 2, 3. Suppose 3 steps, okay? And if I give you more than 4, then you will just stay. If you go, you will go there and stay there, or you stay at the beginning and to the end, right? It's fine.
I don't understand the constraint set.
Constraint set. Okay, this is my general notation. Constraint is just at any given location, the place, the visit, is just this example, right? Do you understand this example? If you are at A7, that's your current state. The control action you can take is 3. You can either go A1 or A8 or A6. Okay? But if you are here, let's say if you are A2, let's say if you're A6, then your control action you can take is A7 and A5. Okay? It's different, right? At different location, the next location you can visit are different. Okay? So the reason I'm writing this, you can see this is the same formulation almost from the previous one. Although previous one I write down the more explicit formula, it's the same almost. That means most of the problem, although from the beginning it looks like looks like a completely different problem, but eventually I can all convert them to this general form. So now I can focus on this general form to study how to solve this kind of problem. Then I can solve a wide range of problems. If you look at this equation, it's the same cost function. It just have different meaning in this case, right? But exactly here, all these things can be viewed as uk belong to u of xk. Okay? It's just at any given time, your control action available to you is different. You need to specify that constraint side. That's the case, right? It's the same kind of mathematical formula. Of course, the variable means different things in different applications, right? So that's the generality of the optimal control formulation. I'll give one more example. Then I think you need to have a concrete understanding of what these symbols mean. Yes?
So why you determine the value of n?
Say that again?
How do you determine the value?
These are parameters of your control problem that you need to specify. There's no how, it's formulate. It's depending on your problem, depending on your objective. In this case, I don't care how many steps. I just want to go there. So I can give any time 4 or 3, more than 3 is fine in this problem. Okay? So these are a parameter that you need to, you have freedom to design. The third problem is motion planning, a simple motion planning problem for autonomous or let's say mobile robots. The fancy name is autonomous vehicle, but it's just a robot, has been studied 30 years. Okay? Let's consider any kind of a mobile robot or autonomous vehicle. It have a model. Let's use a simple kinematic or so-called unicycle kinematic model. And the state has the following. And this is often used, by the way, for mobile robots. I mean, you may find them useful not only for understanding this formulation, but also understanding your mobile robot problems. Suppose this is my location. This is my P1. This is my P2. Okay, I have a car that's the robot. Okay, the robot has, well, I can consider many things. I can model a robot as a bicycle model or as a point mass, as a bicycle model, as a unicycle model, as a dynamic unicycle model that you consider forces. But in this case, it's kinematic. We don't consider forces. We only consider the kinematic information that include the location and not their velocity. So here is, let's call it theta. This is a heading angle. It's this is the velocity. Okay, this is the heading angle. Okay, this is the heading angle that can be controlled, by the way. Right? You can control in different ways. Let's abstract it as you can control it. So the state are 4. You can planar x position and y position. Also, you have theta, and you have velocity. And in this case, velocity can be changed as well. So I want to specify my notation here. X dot equal to v times cosine theta. So this is x dot. All right. You can use simple check matrix. You can find it out. the P change equal to V times cosine theta along the x direction, and this is sine theta. And of course, this is my what? P x dot. This is my P y dot, right? The third one is theta dot, okay? This is theta dot. The last one is how fast you change your heading angle, and this last one is the V dot. So how you can also accelerate. Any questions? That's a model that describes your location. There's different ways to view this. This is one model that has been used quite a bit. Let's use the simplest model, okay, unicycle model. You can consider steering angle, that would be also sleep angle. There's a lot of different things that you can consider. That more details you have, the more accurate. Suppose the model is correct, then the more accurate. But here is roughly, I can also consider point math. That's fine. But here is the unicycle model, okay? My question is the following. Our goal is given a reference, PD, VD, QD, theta D. What are they? So the position reference and the velocity reference, and also maybe heading angle reference. Okay, suppose I gave that. That's specified, typically. Let me give a comment. Those are typically given by planning problem. This problem is tracking control, okay? I shouldn't call it motion planning. This should be called tracking control, okay? So given by planning algorithms, for example, if suppose your vision tells you these are the lane, and you want to stay in the center line of the lane, typically, and those are typically specified as polynomials. Okay, you want to specify your desired polynomial. You know the lane roughly, and you want to track that. You want to stay in the center. That's your objective. So you can find those position and its velocity and heading angle changes. Okay. Let's assume they are given now, and our problem is track. Problem is to track. Track a given reference. So the first of all is this is continuous dynamics. I'm not sure whether you can see it. This is my vector field. Okay, let's view what are the controls here. The rate of the heading angle change, the heading angle change rate, and also the acceleration. Okay, the velocity change rate is something I can control in this case. And so that will be my x and u. I assume you know this is my u1, this is my u2, right? This is two u's. I mean, that's specified. Those are not state, those are controls. Okay, your control directly control the velocity of certain state. So then that will be my, we want a discrete time model. That will be xk plus 1 equal to xk plus, if you use Euler discretization, that will be xk uk times delta t, right? And this whole thing is my f xk and uk. This is called d, the discrete time. Are you with me? You have a continuous vector field you can discretize with sampling time. Then you have a discrete time thing. Mathematically, this model has the same representation as the previous shortest path problem on discrete graph. You see, it's all the same thing. That's why the framework is powerful. It depends on how you view the meaning of different state and control. They will represent different problems, but mathematically they have the same representation. Okay, that's the beauty. We want to track this problem, how to formulate. There's 1,000 ways you can formulate. For example, I will throw out one formulation. For example, you can say I want to minimize running cost. Suppose my running cost is 0 and minus 1. Suppose my running cost will be pk minus pkd. You want to follow your desired, right? You want to minimize that. Plus, let's use maybe, I think control is not that important. I would say 0.5 times alpha k. Alpha k is my control, right? So it's alpha k is my uk of 1. Alpha is 2, right? Alpha is 2. uk of 2, that means alpha k, right? And plus, suppose I also want the change rate to be not too big. Let's say this is a 2 times uk of 1, uk of 1, subindex 1 squared. This means I don't want the change rate of the turning to be big, right? Acceleration can be a little big because I penalize the changing rate of the heading angle to be larger than others, okay? The cost function, and also I want to penalize deviation from my theta k minus theta kd squared. Well, there could be also terminal cost as well, but subject to, let's say xk plus 1 equal to xk plus fxk uk delta t, which is my discrete time update equation, and also uk belong to u. You need to specify what control action you can take. For example, you need to respect turning radius limit. I don't want to write down everything completely. In this case, roughly you need to consider a lot of things, how fast you can change. For example, the acceleration cannot be too big, things like that. And also, you also want to maybe be safe. For example, I can put that in the cost. I want to plus 100 times my distance to obstacle. Okay, suppose that's my current position, pk. You see what I mean? This is a function that how far you're away from distance. Your perception will tell you, okay, there is a wall or some obstacle, and you can calculate based on how close you are to that obstacle. You can calculate a number. The larger that number is, the safer you are. But you have too many obstacles, you need to penalize them. Okay, that depends on the current state as well. So all these things, I will circle this out. These are part of the state. These are part of the state. This is part of the state. Okay, so all of them are in my formulation here. All of them are running cost. You see what I mean? All of this whole thing is a running cost. That means it depends on xk and the uk only. At any given time, the running cost depends on the state and the control. The terminal cost depends on the final state. Well, I can keep adding things. That depends on your boss. Okay, he may care more about comfort, care more about other things. You need to put that into your cost functions. And there's some tuning about the weightings about different cost functions. Right? Some people use reinforcement learning to solve this, which is exactly the same. It's just different ways to solve this problem, but they are all solving optimal control problem. Okay. I hope that's enough formulations, and I can just assure you that all the problems you care or you want to solve can be formulated as an optimal control problem. Let me repeat. All the control problems you're trying to solve can be formulated as an optimal control problem. I hope that maybe each of you will give you a homework. You can try to challenge me by writing down a problem that you think you want to solve, but they cannot be formulated as an optimal control problem and sent to me, and I can tell you answer next time if you want, right? All the control problem, okay? Okay, that's the formulation. That's already a big deal. Okay, you can formulate this, and then there are packages that can help you solve optimal control problem. You know, I don't like you to just call packages. I want you to be able to write your own package, at least know what's going on there. So we have to learn a little bit about other things. In particular, I will give you a short, I would say very, 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 very short introduction to dynamic programming. And how many of you know dynamic programming? I think everyone, right? No? you know that. 小韩 知道 和 know. It's know of, but don't know, okay? Dynamic programming is like coding. 规划哈，动态规划。Linear programming, dynamic programming. Programming means 规划, okay? So dynamic programming is the most important tool for solving deterministic and stochastic optimal control problem. If it is stochastic, then it's related to learning already, okay? You can use reinforcement learning or Q learning. They are all related to optimal control problem that we are calling about. Okay, they are the same. Let me repeat. All the learning or reinforcement learning or Q learning or DQN, AlphaGo, they are solving what? Optimal control problem. You can find their running cost. You can find their terminal cost. Exactly. So AlphaGo is similar to our road network problem. I mean, based on abstraction, but of course it's hard to solve. So divide and conquer. So the key idea, I think it's just algorithm optimal control problem can depend on n-1 optimal control solution, which in turn depend on n-2. So it's keep like that, right? It's backward induction. We'll see how this works. I do want to emphasize this is all the thing, the dynamic programming. There are different views. Okay, you may learn it from I think most CS theory class will teach of dynamic programming. How many of you have learned dynamic programming from other class? Algorithm design. Really? We have this class? In CS? In CS, okay. So typically CI would cover this, but it will cover it differently, typically. They care more about implementations. Okay, they will learn things a little different flavor, but in nature, mathematical nature, they are the same. Okay, I want to mention that so the DP, dynamic programming, is based on Bellman's principle of optimality. So this means how do you know something is optimal or not? So typically, when we do least square, we take a derivative, make it equal to 0. That quantifies or specifies something is optimal, right? But that is called variational optimality condition. Optimality condition. What do I mean by that? So if this is your trajectory, if you perturb a little bit, if you bring this, it won't be optimal. Okay, that means infinitesimal perturbation will be 0, cannot improve the cost. That means typically the gradient equal to 0. Things like that. That's variational type of optimality. But in Bellman's principle, it's a completely different way to specify optimality. There are different ways to think something is optimal or not. You just need to remember. So for example, what does this mean? Any segment among optimal trajectories is also optimal among all trajectories joining the two endpoints of the segment. I'm not sure whether that's my summary, by the way. If you don't understand, I can explain. So suppose from here to here, this is my optimal. This is my optimal path, okay? Then I ask you a different problem. I ask you, What is the optimal path from here to here? It will be exactly the same path. You see what I mean? Let me repeat. Suppose this blue line is optimal from A to B. And I ask you, and this C and D are on the optimal path. I'm asking you, what's the optimal path from C to D? Of course, you should follow this path. What else? What if? So what happens if not? If there's other better path, let's say this is a better one, then my optimal path would also take this, right? That's roughly the same. That's roughly the meaning of Bellman's principle of optimality. Any portion of the optimal path has to be optimal. Otherwise, you will replace that portion with other things, with a better one. I don't think you need to fully understand what it is. It's just keep that in mind. That will be okay. All right. So let's jump into dynamic programming. So in order to solve, our goal is to solve. So go solve n horizon optimal control problem. Okay. OC, optimal control problem. And we start by defining a sequence of optimal control problems with varying horizon. One is Vj. It means J can be 0 or 0 horizon, 1 horizon, 2 horizon, 3 horizon, up to n horizon. Is that okay? I just replace n with J, all right? But my goal is to solve n horizon problem. But I start from the 0 horizon problem because the smaller the horizon size is, the simpler the problem is, right? So that's roughly the case. So there's a few kind of, I will call it terminologies I have to ask you to know, and you have to know it. I think that's very important. One is called value function or cost to go. Have you heard about this? It's called a value function. So what does this mean? What does this mean? Vj of z means the optimal cost for the n horizon optimal control problem. So if you have, let's say, if you have, I want to say, minimize x squared plus 1 over x, suppose, right? And this is my fx, right? And so the minimum value would be 1. No matter what x is, it will be 1. So minimum value, this is the value function, will be 1. Okay, the optimal cost it can achieve is 1. So this means the optimal cost, you solve this optimal control problem, you will have a cost. That cost could be number 1 or 2 or 3, and that number is called the value of the problem. Why it's called the value function? Because the problem changes when the initial state changes. As I mentioned, this problem depends on the initial state. Okay, the optimal cost, I can just, let me finish by this. The optimal cost, if I start initial state, is A2, A8, or A3, or A1. The optimal cost will be different. The optimal cost will be completely different. If I start from here, then optimal cost will be 0. If I start from A1, the optimal cost will be something, A8 will be something. Overall, the optimal cost it's become a function of where I start. So that function is called optimal value function. It's called value function. In this lecture, we will call it V star, right? Let's take a break. Okay, let's continue. Again, I want to emphasize the value function here is the optimal cost of the problem. And the problem depends on two things. One is where you start, what's the initial state, as I mentioned before, and also how many time horizons you give to this problem, which is J. So this meaning, the true meaning or complete statement of this meaning is the optimal cost if there are J steps left and you stay at the Z. You know this is J and this is Z, okay? If you're currently at Z and you have J step to go, then this is the optimal cost to finish the rest of the horizon, okay? And these are the solution, optimal solution to the above problem. And let's, there are different ways to do dynamic programming. One way is called value iteration. I think this is the only way we are going to learn. And it's the most popular way that you're going to code as well. What is value iteration? It's just you completely compute the value function from 0 horizon to 1 horizon up to n horizon. Okay, let's start from it's like a recursive. You still have a starting point. The starting point is n equal, or the horizon size equal to what? J equal to 0. So what do you think is the J horizon problem is? Let's look at this problem. I'm not sure whether you can understand when J equal to 0, what are the optimization variables? These are the generic terms. Okay, the generic terms. When J equal to 0, you have U0 up to U minus 1. Do you have anything? You don't, because you don't have any index satisfy the indexing rule, which is from 0 to J minus 1. So there's no controls, right? What about this summation? There's nothing, right? You only have one horizon. There's no running cost. The starting time is the end time. Okay, so but you have G of X, J equal to 1 is X0, right? So X0 is Z. You don't have any, all the other constraints are satisfied. They don't appear anywhere. So when J equal to 0, we can say V0 of Z equal to G of Z. That makes sense. The optimal cost to go, if only 0 steps, is the terminal cost, because at the beginning you're already at the terminal time, right? So that's roughly the meaning. Okay, so V0 of Z equal to G of Z. So we don't need to compute. We can directly write it down if we are already determined the terminal cost. Okay, let me jump a few steps. Let's just say it's recursive, right? So now we know how to start. When there are only 0 horizon, then we have terminal cost is the value function. What about suppose? Now let's directly jump to here, okay? Suppose we have Vj of Z. Suppose we know the cost function or value function, J horizon value function. How can we compute the J plus 1 horizon, the optimal control cost?
All the possible passes to the GZ, we choose the smallest.
Okay. Let's look at this figure. Let's just look at this figure. I know you don't like derivation. Let's look at the figure. I'm giving you a problem. Suppose this is my J horizon problem, right? Now I'm consider J plus 1 horizon. My horizon size increased by 1. Okay, suppose I have to solve the J horizon problem means what? I know this thing. That's what I given, right? Vj of Z. What do I mean by that? I already solved it. I know the optimal cost. if I have j steps, my initial state is z. Okay, that's already solved. And suppose, well, the z can be different, right? The z can be different. Suppose there's a 2z possible, z of 1, z of 2. That's two different state. If you start from here, I know the optimal path is this. If you start from here, the optimal path is this. That's from the figure. Now I'm going to give this figure some number. Suppose this is 20. This is 100. Okay? That's the optimal path. Has 20 cost. Okay, this guy. But this guy, optimal path, although it's optimal, but it's still pretty big, is 100. Because at the initial state is different. Are you with me? So these two guys, which one is a good initial state? Z1, right? Z1 is a good initial state. Z2 is a not so good initial state for a J horizon problem. Okay. Now I'm consider J plus 1 horizon. So suppose I start from this Z, capital Z. I have two choices, suppose. At any given state, you have different control actions available for you to make decision. Suppose at this Z, I have two choices. One is U1, the other one is U2. Which one is optimal? Well, that doesn't mean no. I don't think so, right? It depends on what number I gave you. Right? It's hard to beat. It could be this guy, this step is 100, this step is 1. Okay? So take this one step, may give you 100. Okay? And take this step, will give you 1. And overall, after this step, which one you should take? There's different paths as well. You should definitely take this, right? That's Bellman's principle of optimality. I already solved this problem. I don't need to resolve it again. I know from Z2, this is my shortest path. So what would be my Vj plus 1 of Z in this figure? What's the cost number? Depending on which path I take, right? Suppose, which one is better? This is total cost is 120. This total cost is 101. Which one is better? This path is better. So the cost would be 101. This is my value function. Right? This is my value function. So you should take down here. Well, that depends on, as I mentioned to Yuntian, that this depends on my number, right? Suppose my number is like, I'm going to test you. This is 5, this is 10. What's my optimal decision? What's my U of 0? This is time 0. J plus 1 horizon time 0, so I should take action. Which action I should take? If I only look at this one step cost, this running cost, then I should take this guy, right? I should take 5 because that's give me my most smallest running cost. But taking this step will cause me to a very, very bad initial state for the J horizon problem. All of these particular step, I save some cost, but later I have a larger cost to go. Okay, so if I consider not just one step, this is called greedy, right? You only consider next step. If you consider today's happiness, you will play games, right? If you consider the happiness after finals, you will study, right? Okay, that's the you should consider what? You should plan. You should think if you play games, you will enter a worse state. Later on, you'll have more time need to spend for a class and the GPAs. Your entire life depends on your everyday's running cost, what decisions you make, right? Of course, today's happiness is also important. Okay, so I hope that's fine. So in this particular number, let's write down. Let's give you one more case. What is the optimal value function for j plus 1 with this initial state. In this case, number 30, right? So that's 30. Because you should go here. All of the first, today I'm going to suffer a little bit, but later I'm going to have a really small cost. So overall it's 30. So you know how to make decision now. What do you need to compare? The running cost, just one step, plus the future cost of the next j step cost, optimal cost. Does this matter? Does these two curves matter? Maybe I have a lot of other curves. It doesn't matter anymore because I already sort out those things are not the optimal ones. I don't need to worry about them anymore. Okay, I only care about start from this, what's my optimal cost, okay? I think that's the figure. If we look at the equation, that's the following. Okay, so available at time 0, if j plus 1 cost is u1, u2, and what we did is mathematically what we're doing. What we're doing is comparing the sum of running cost plus the future cost. The future optimal cost. If I apply this step, then I will be at different locations. This is what this means. Fz of u1 is nothing but z of 1. If I use u1, I will enter here. This is right, z1. If I use u2, the next step I will be here. Where I am, next step is super important because that determines my future cost. So I need to compare these two numbers. I pick the small one. That's my optimal decision at this stage. Okay, so mathematically, my optimal decision is what? It's whichever these two, so u1 or u2, depending on which one I am, right? And it's argmin. What does argmin mean? So the mean of x2 plus 1 is 1, right? Argmin of x1 plus 2 is what? 0. Is the minimizer minimizes this cost. Minimizer means x equal to 0. That's 0 is the minimizer. In this case, if I look at this number, in this case, mu j plus 1 of z equal to what? U of 1. I should go up. You see what I mean? At this step, I should go up. That's my optimal cost. That's my optimal decision at this time. And the overall optimal cost is this running plus the future. So the minimum cost is nothing but I minimize over all the possible control action I have at this stage. Okay? And what I compare, the running cost, just immediate satisfaction, right? Today's happiness, plus the future suffer, the future cost, right? But you take the optimal, you only care about the optimal ones, right? So you don't study today, and you assume tomorrow you study in the optimal way into the next, until the final. That's your cost, right? Versus you study today, I mean, well, anyway, I know you don't like study. It depends, right? So I don't like study for the exams. I like to study to understand things. I think everyone has its own curiosity. Okay? We like to study you can Google all the time to satisfy your curiosity. Maybe that's about pop stars. Maybe that's about some kind of knowledge. But that's fine, that's curiosity. We like to study to satisfy our curiosity, but we don't like to study for some kind of exam. But sometimes this is the way we learn, right? You have to have some pressure to learn. I think, so this equation, does everyone understand this equation now? Vj plus 1z equal to mean of available control mean over all the possible control actions, and what kind of metric I determine which control to use is running cost plus future optimal cost. Your current decision will affect your what? Your next state. It depends on whether you are in a better or worse position for the future cost or future remaining decision problem, okay? And this particular equation is called Bellman. Okay, it's Bellman equation. No, that's not a Bellman equation, it's Bellman recursion or whatever. Okay, it's value iteration. Well, anyway, so value, this is just value iteration. Sorry, it's not Bellman equation. Value iteration. That's exactly value iteration. We already learned value iteration. And these two has different meanings. We all know this guy's meaning, right? If you currently have at state Z and you have Z plus one horizon to go, then that's my best cost I can have. And this guy is the corresponding best control action I need to take, okay? So I need to explain a little bit this guy. It may be confusing for some of you. This is mu, not u. You know mu and the u different, right? Mu here is a function of state, which we call control law or controller, okay? Versus control action, that's the particular number the controller will output, right? This is a control law. It depends on, this is optimal control law, okay? It's a function of state. It depends on where you are. It depends on where you are. For example, if I'm here, this path will be my optimal control, all right? And if I'm here, well, this path will be optimal control. My optimal control depends on where I am, and also depends on where, how many steps I have. Okay, so if tomorrow is the final exam and you didn't learn anything yet, maybe the optimal control for you is to play games, right? Your GPA will be the same, right? So, but if your final exam is 10 days away, then your optimal decision today maybe still play games, but maybe study a little bit. That will be different, right? As the time horizon also determines the optimal action you need to take. I'm going to test you with these are control actions, right, to solve this problem. I'm going to test you my notation now, okay? So this guy is initial state x0 equal to z, suppose, right? Then I take the optimal control actions, so that will be my u0 star. If I apply u0 star, I will be at x1 star, which is f x0 u0 star. If I apply my optimal control action, that will be my optimal state next time. Then I will apply U1 star, that's my optimal control at that time, right? Then I will be optimal 2, so dot dot dot. Eventually I will be at optimal xn star. That's my optimal trajectory, the system state trajectory, okay? So now I'm going to ask you to change the notation now a little bit. Suppose this is n horizon, okay? J equal to n, all right? That's n horizon problem. I'm asking you, this is the control action I take, right? If I have n steps left, I'm currently at z. So u0 star eventually, by my next notation, will be this of z star, okay? So this is the control law, okay? And if I have n step left, I'm currently at z, that's the control action I should take, okay? That's the play game or not, that's this guy. And this guy means play games. This is a law, okay? The law depends on how many days you have, and also depends on readiness for you to take exam. If you're just missing a little bit, you will still study. If you didn't learn anything yet, you will just give up, right? So that's it depends on how many days you have, depends on your readiness, depending on where you are. Now I'm going to ask you, what is this? How many steps I have left? N-1 optimal control action, where you are? X1 star. Okay, so this is U1 star. This is the second step you take, the optimal one, but it's equal to the optimal control decision you should apply it if you have N-1 step left, but you are at X1 star. Okay? This sequence was determined by solving an n-horizon optimal control problem. But as I mentioned, Bellman's principle of optimality. If I look at this n-1 horizon problem, this will become my first step to take. Okay? You see what I mean? If this is I only consider this problem, then this will be my first step to take. And this X1 star will be my initial state for a J+1 problem, so N-1 problem. And this guy will be the optimal control. So this law is nothing but my notation, okay? It's nothing but the optimal control action I should take if I'm here and with N-1 step left. Say that again.
Why it doesn't concern the X0 and X1?
The X0 or not is kind of a dummy variable. So okay. If you recount your starting point, so if I have J+1 problem, I'm currently at here. So time changes, right? Time changes. This will be your X0 at time 1. If you start your problem at time 1, then X1 will be your X0. Let's do that anyway. X1 will be your initial state. Okay?
We are already believe the optimal trajectory based on Bellman's law.
Yeah, of course, yeah.
But I think maybe
So this will be your NJ horizon. So that's why I call it Z. This is my Z for a N-1 optimal control problem. Okay? So that's a function. So I can start at any given time. All I need is that this function. This is a function. This is a function of initial state. Depending on where you are and how many steps you have, this function will tell you the optimal control action to take. All right. Let's look at an example. I think that will be. I don't think it's much better, but. A little bit better, okay? Here is some kind of summary. All right, so time 0, you're here, control action, this is X0, but this is what? This is the optimal control action. If you plug a law, that's the optimal n-horizon control law, okay? So I think I have an explanation here. That's this thing, what's the meaning? It's the first optimal control action for a J+1 horizon problem with initial state Z. Or it is optimal control action when the system is at state Z and there are J+1 steps left or to go. It will take some time for you to think. I think at least you have rough, vague understanding, maybe not complete, but that will take some after-class effort. Let's try to solve this problem. All right, at least we solve some problem. This is the problem, the simplest problem, shortest path problem. We can code. The coding will be few lines. Okay. Now I'm asking you, based on my formulation, we start value iteration, right? What is this? This will be my terminal cost, which is, suppose I want to go to A4, right? This will be 0 if Z equal to A4. It's infinity if z does not equal to A4. Is this a function of z? Of course, it's function of state. It really depends on where you ask for the optimal cost. Because the function, cost function, the value function depends on the state. At different state, you have different value function. Oh, sorry, the number, the value of the value function is different. Okay, now let's look at the. Any questions?
If C doesn't equal to A4,
It's infinity.
why?
I just don't. Well, you can make it. You can say it's he thinks it's y. I can say it's 10. If you didn't get there, I kind of gave you a fine. It's $10. But for me, I think I just want.
To make sure.
That means you are not there. Or in MATLAB it's NaN, whatever I want to. I just say you didn't get there. That's a discrete thing. It's success or not. Success is 0. If you didn't success, you died. You're dead. That's infinity. That's my cost function. You can have a different cost function. Okay?
Why do you define it as?
Let's work on a few steps. You will see why that's reflected the shortest path problem. Okay? I don't think we need to redefine. We already formulated the problem at the beginning of today's lecture. What about V1 of Z? So we already know V0 of Z. What about the value iteration formula? That means from U of Z, the running cost plus V0 of F Z of U. That's the value iteration formula. Let me repeat. This is the value iteration formula we just explained with that figure. Today's happiness will lead you to some state which is Fx Fzu, and start from there you take the optimum cost. But the horizon decreased by 1. You have 1 day shorter time. Okay? So let's look at example. Let's say V1 of depend on what Z I'm asking, right? Let's say V1 of A3. What is it? That's minimized over the possible contractions I have. A3. Where is A3? Here. I have 2 actions to take, right? So that will be. I need to compare 2 contractions. The first one is L, A3, I go to A2, right? A3, A2, plus if I add A2, but I only have 1 horizon left. But I try my best, start from there. That will be A2, right? That's F next time will be A2. In this case, I will directly plug in A2. Sorry, that's one action. Okay, the other action is A4. I need to compare this guy. A3, A4 plus V0 of A4. Okay? I need to compare this number, 2 numbers. What are they?
What is the furnace here?
This guy is a 3 plus infinity. Why this is infinity? You plug in, it's infinity. Okay? This guy is. This is 5, okay? So 5 plus 0, so it's 5. So overall, I have 5. Okay? And my mu1 star A3, what is it? Again, what does it mean? If I'm at A3, I have 1 step to go. My optimal contraction is. This means I take A2. This means I take A4. So the optimal control is A4. What does it mean? If I'm here, I have 1 step to go. I need to directly go to A4, of course. Okay? That's my optimal action. But the action depends on where I am and how much time I have. Let's see, one of, let's say, what about A5? There's 3, but I don't think, but repeating this, you know this will be what? 2, right? Because you should directly go here. This is 2, and A5 is 2, A8, V of A8 is 5, right? And what about V1? What about V1 of A2? V1 of A2, you have 3 choices. All of them will give you what? Infinity, infinity, infinity. 3 choice. Mean over this 3 choice is still infinity. So what about V1 of mu1 of A2 star? What is it?
Either is optimal. Any is optimal.
Equally bad, right? Equally bad. I can randomly pick one, or I can. It's hopeless anyway, so right. So I can pick anyone. All right. I can pick. Let's say I can just pick A3, A2 as well. Anyways, will give me infinity according to my cost. So overall, I will have V1 of Z is a function. This function, what does function mean? You have to define its value for all the possible Z. How many possible Z I have? 8. So, but it's 2 if Z equal to A5. It's 5 if Z equal to A8. It's 5 again if Z equal to A3. Is infinity otherwise. Oh no, sorry. It's 0. It's 0 if Z is A4, right? If only have these 4 finite values, all the others are infinity. The more important thing is the following. We have time for quiz, right? What is it?
Yeah.
Have 5 minutes? Okay, that's good. V2 of Z, let's do one more, right? V2 of Z is minimize. You first write down the value iteration formula is U belong to U of Z, LZ of U plus V of what? 1 of FZ of U. The running cost plus, if you take this contraction U, you will be at the next step. And after the next step, you have only 1 horizon to go. But you already compute everything you need for 1 horizon. So you can just do this. And I wouldn't write down everything. Let's pick an example. V2 of A2, suppose. You don't use your intuition. Don't use your intelligence. Think yourself is a computer. That's it, right? You think yourself is a computer. What you need to do is the same. It's just minimize. You find out how many actions you have. So the mean of A2 at A2, how many actions you can take? 3, right? So you need to compare 3 numbers. Okay, the first one, if you take to A1, that means that's L A2 A1 plus V1 of A1. That's the first. L A2 A3 plus V1 A3. Of course, you can stay at A2 as well, but well, maybe that's 4, okay? L A2 A8 plus V of what? Of V1 of A8. A8. Okay, let's just use these 3. The other one, I don't think we need to. I mean, this is fine. What is it? This is a 4 plus. Think yourself as a computer. You don't know what are these. You have to compute them in order to know which one to take. This one is A3, A2, A3 is 3 plus 5. Now you have finite value, right? That's why you need to compute V1 for all the possible Z's. You're going to use all of them. Not all of them, at least you don't know which one to use, so you have to compute all of them. And this guy is A3, A8, this is a 3. The number is really bad. Why there are 2? Those are 5 as well, so it's 8. So overall, minimal is 8. The value function is 8, and the mu2 star A2 is which one? A3 or A8. In this case, they are the same, so I don't care, just pick one. So we will say that we need to we need to compute. The computer is that. It reminds me to do a quiz. I can't do quiz anymore, so it's I would say you should write, we need to compute this for all the state Z. Okay, not only these two, and keep going like this. That's called the value iteration. All right, that's I think we finished today's. So I would continue our discussion from last time about optimal control. As I mentioned before, all the control problem can be viewed directly or indirectly as optimal control problem. Let me emphasize all the control problem. You can think of them as optimal control problem. So that gave you a unified framework to think about all the decision or control problem in general. So that's why typically optimal control is the most, I like it the most. I don't know whether other people. And if you see any fancy robot from Boston Dynamics, all of them are based on optimal control and model predicted control. They are related as well. Okay, and the last 2 lectures, we covered basic foundations for optimal control formulation and the DP, dynamic programming. Let me briefly recall, it's from last week, so it has been a week. Let's review or recall the formulation a little bit. Optimal control formulation. A lot of people like to see the diagram, like to see figure, okay? You have a system or plant. You want to design controllers to control it. That's all we're trying to do. Okay, and the control means you need to send the input and you can measure the output. Typically for optimal control, we assume we have the state. If you don't have state, you can do observer design to estimate state, okay? And that may be the output function that give you yk, right? And so typically we will design a controller, oftentimes controller, and you may know, okay, there's a PID control, right? That's maybe all you know. We learned pole placement, right? Maybe negative k times x, something like that. Okay. Feedback going here, that means this part is called controller. Okay. And at the beginning of this lecture, I told you that a controller, if you think about mathematically, is nothing but a mapping from state to a control action, right? Controller can be viewed as a function. However you want to define, you can, if you do coding, right, your function could be 10 lines of code or 1,000 or 10,000 lines of code, depending on how complicated that function is. Okay. In optimal control, and this is our optimal controller. Optimal controller is a controller. It's still a mapping from state to control input. But in determining the control input, this means the output of the controller is the control input to the plant. Okay? If I want to determine this controller control action, I want to solve a optimization problem or optimal control problem. In the way I want to minimize certain cost subject to some constraint. If I want to have more details, let's say my system, this is my block system. And in general, I have too many colors. Let me stick to black. In general, I have a nonlinear state update equation and may have an output equation like this, right? And we do not consider, at least we do not consider systematically about uncertainty. There's no noise like a Kalman filter. This is just deterministic case. That's the system dynamics. Okay. The optimal controller part, this part, that's the optimal control part. The key idea is what? It's to encode your control objective. If you want to design a controller, you must have an objective. You may not know your objective has a mathematical form or can be written in a mathematical form, but you do have an objective form, right? A control objective. You want to encode your objective into a so-called cost function. In the learning community, they like a reward. In control, I like cost. One is the negative or the other, okay? So cost function. In reinforcement learning, this will be reward. They want to maximize reward. We want to minimize cost. Then we find the optimal one, okay? Because we have a criteria now, we can determine what are good, what are bad, right? In particular, we want to find the good among the good, which is the best, okay, or optimal one. So we want to have the optimal control. U star, typically this will be U0 star, U1 star, all the way to the future, depending on how long the control horizon is. And to minimize the cost, okay? That you, two steps, right? You translate your control design objective into a cost function. Then the design of a control becomes solving this cost minimization problem, okay? Under what condition we can do this? Under no condition. All the control problem you have in mind can be formulated this way. You may not realize it. I think that's very important. You have to know whatever you want. You say, I want to my car to go from A to B without hitting the curb or obstacle. That can be formulated as an optimal control problem. You minimize maybe the traveling time or fuel consumption, and subject to constraint that you stay away from the obstacle. Okay, as I mentioned before, you can, if you don't believe this, you just come up with something you don't think. You can write it down as a mathematical form, then you send it to me, and I didn't receive any email yet, okay? So I can try to go through that with you. Okay? So that's why it's so powerful. It's very important. And typically that means, well, how do I represent my objective through cost? And a general framework is the following. general cost function structure, cost function, which is J of terminal cost, J of cost. Cost is a function of initial state and the control action or control sequence you want to take over a certain time horizon, k from 0 to n minus 1, L, xk, uk, plus g of xn. This is called terminal cost. Okay, that's the final cost or terminal cost. When you are at the end of the control horizon, you have no life after that, okay? And you evaluate how good or bad your life is at that state. Okay, there's nothing you can do anymore, okay? And this L is called running cost. Okay, so these two encodes all our objectives. So for some control actions, you don't care about running cost. You don't care about each step where you are. You only care about you reach your final goal, which is a particular state in the state space. Okay, so and if I have this cost function, my optimal control problem is what? It try to minimize what? J of n of z of u, minimize over all the possible u. This u is a sequence. It is class. Everything is a vector. Everything can be a sequence. And this is a sequence, all right? And you are not free to select your control. Your control has to satisfy the so-called constraint, 约束，对吧？What kind of constraint you have? Subject to. First of all, dynamics, right? Dynamics. So it's xk plus 1 equal to fxk uk. Okay, why we care about this? Because control actions determines, along with the initial state, determines the whole state trajectory. So if you determine your control, if you decide what the control is, then the entire control state trajectory is determined already. And that will affect your cost because your cost function depends on the state as well as the control action. You can also have a control constraint, like the current cannot be too large, your voltage cannot be too large, things like that. As I mentioned, your control constraint can be state dependent. At this particular time, the available control action you can take, that's the set. I think I gave examples, right? If you're close to obstacle, your available decisions are limited, right? If tomorrow is the exam, today your action choice is different, right? You can only memorize a few formulas without going through all the notes. So that's exactly what this means. And also xk, they also have some kind of a state constraint. For example, maybe temperature is your state. You hope your temperature would not be too large, or your velocity cannot be too large, things like that. Okay, so that's overall. You can think about them as a high-dimensional optimization problem, or we can view that optimal control problem. Optimal control problem can be viewed as optimization problem of dynamic code systems. Okay, so to do this, we introduce the so-called what? DP, dynamic programming, right? So, so you should know the solution of this is called V star or V of Z in. This is called the value function. What does this mean? The optimal cost. Okay. Because this is a function, this cost function depends on the initial state and the control sequence. If you minimize over the control sequence, this guy will be chosen to be the minimum or the best one. You substitute the best one, that becomes only a function of initial state. and that is called optimal cost goal or value function. What is the meaning of it? If there's n horizon, and my current state or initial state is z, then the optimal cost, not the control action, right? The optimal cost is this Vn of z. We gave example before. Okay, in order to solve this n horizon problem, and we can do value iteration, and the key is to determine what? We start from 0 horizon, and 1 horizon, 2 horizon, okay? So in general, we have, say, j horizon problem. That's called j horizon problem. And I can call this part my equation, hold on. I can call this constraint equation C, okay? So I can define this as a Vj of z equal to minimum over u of jj of z. Also have u. In this case, it's u. If I want to write more explicitly, that will be u0 up to uj minus 1. Okay? The first action you take is u0, and then the last one you take is j minus 1, then you move to j. Okay, that's the cost function. If you just replace this capital N with this j, that's the cost function structure, and I don't want to write down everything that's subject to what? The constraint. Equation constraint the same. The same constraint is. So we can start from j equal to 0, right? That's called the value iteration. And the V0 of z equal to, as we derived last time, that will be g of z, the final or terminal cost, because you're already at terminal. You didn't give any choice. You just, at the beginning is your end. The beginning of your life is the last day of your life. It's things like that. You have no control actions. All right, so that's the terminal cost will be your 0 horizon optimal cost. Okay, and like any induction, you just need to move from j to j plus 1. As we mentioned before, this is called value iteration. Okay, so Vj plus 1 of z is, what is it? Minimize over all the possible control action you can take at this state, at current state. So u belong, this u is one, it's just one shot, one time step u, okay? Capital U of z, that's at this particular state, you have this amount of choice. You can have 2 choice, 3, or infinite number of choice. And for each of these choice, you want to pick the best one. How to evaluate the best? Of course, you can do the running cost. Of course, if you apply this, if you apply this u and you currently let z, you have an immediate running cost at least one step. But at next step, you will take the optimal one starting from next state. So that will be Vj, because time horizon is shorter by 1. You move one step further, which is Fz of u. I think we explained this from different ways last week. Any questions so far? This is called value iteration. That's everything. There's different words describing this. In the CS community, this is called Bellman. I think they call backward propagation, things like that. Okay. So I think before I talked to a CS candidate, faculty candidate in the US, and they talk about this backward. I don't know what that means. So then I argue with him a little bit. Then I find out it's just different terminology between different community. But in essence, the math is the same, right? math is the common language across different domains. I think that's okay, right? So I think last time we discussed this. This is how we derive it, right? Through figure. And today I'm going to derive it a little bit with math, pure math. I don't think either. Some people prefer this way. Some people prefer figure way. Some people just don't like proof anyway. So, but I have to let you know that this is very common sense actually. It doesn't need to. You don't need any advanced math to understand this. The starting point is still the terminal cost. The zero horizon optimal cost is this. And then we talk about one horizon optimal control problem. What is it? You just plug in j equal to 1 now, right? Then you have an optimal control problem, right? You have a one horizon optimal control problem. And that optimal control problem is, I would say V1 of z should be minimized over my current U0. Currently I'm at z, right? Available control is capital U of z. And it's one horizon. So the do I have a running cost? So I have running cost x0, U0, right? The next state is already terminal. So it was g of x1. This is okay, right? This is the plain introduction. Sorry, just somehow rewrite this formulation when j is equal to 1. Okay, so if I want to write dynamics, that's x0 equal to z, that's in my initial state, and x1 relate to x0 and also relate to u. So that will be f x0, which is z, times u0. Okay? So then you have all the relations. So it's only a function of z now, right? Because u0 is something we want to optimize over. If I fix u0, then I know this guy is z, u0 is fixed, x1 is also fixed. Okay, so I can enumerate all the possible u0 I have and find the best one. Okay, so this equal to, you can immediately see in this case that will be min over u0 belong to uz. This is L. Let me put it into general form. I know x0 is z, so I'll just like z u0 plus g is v0, right? G function is u0. I plug in x1. x1 is the next location, which will be fg of u0. I need to write down everything in terms of initial state and also the control input. This is the value iteration, right? This is value iteration. That's too simple. That's one step. Any questions, by the way? No questions. Very simple, right? Let's look at 2. Once you know how to move from 1 to 2, then you can move from anywhere. That becomes a trivial problem then. I think I need more space. Let's see. 2 horizon problem. So first of all, I start from z x0, right? Then I will be applying my pen has some problem. I will come, this is u0. I will go to x1. Then I have u1. I will go to x2. That's 2 horizon problem. How many control decision or control action I need to determine now? 2, right? two horizons, I have two control actions. I need to determine one is U0, the other one is U1. Okay, depending on what I pick, my cost will be different. I want to minimize over my cost. Okay, so let's write down everything. So that will be two horizon optimal control problem. Minimize over U0 and U1. Okay, if I write more carefully, the available control action I can take, U0, belong to capital U, this control constraint, depend on initial state in general, okay? But U1 depends on what? X1, okay? So this X1 depends on U0, you see that? So this is more like complicated now, all right? I need to pick among them what? Running cost first. So L X0 U0 plus L X1 U1. Then I have terminal cost X2. That's the most general or most direct way of writing the two horizontal optimal control problem. Of course, subject to constraints, right? Subject to constraints, dynamics, let's say. I wouldn't want to write them down. A key is that, let's write it slightly differently. Min over U0 belong to U of Z. U1 is a causal system, right? Your tomorrow's action would not, so your today's action doesn't affect your yesterday's dynamics. It's like that. You see, time moving forward. Okay, so then U1 doesn't affect this. So the X0 and the U0, this cost does not depend on U1, right? So I can move this inside. X0, U0, and plus min over U1 belong to U X1. Okay, and these two terms depend on, well, depends on both U0 and U1. Okay, so that's X, I will say X, Lx1 U1 plus G of X2. If I substitute dynamics, then that will be F Z or X1 now. X1 U1, okay? Do you see what I mean? Now, if you have, let's say, minimize X and Y, you have X squared plus 2X plus Y squared. You can do things that this term only depends on this. You can, maybe this times X, it's fine. You can separate them, all right? That's essentially what this is. So this term depends on what? Depend on both U0 and U1 and Z. That means X1, X0. Because it depends on X1 and also depend on U1. X1 depends on X0 and U0. Okay, so that will become U0 belong to U of Z. And now I'm going to change, all right? Because X0 is Z, right? I will say Z U0 plus, I'm going to tell you that this one is nothing but this guy. Okay, this depends on X1, right? If you parameterize this problem with X1, it's nothing but this is what? V1 of X1. Okay, if, let's say, if you substitute this Z with X1, okay? If you substitute this Z with X1, then everything is the same. Of course, this U0 is a dummy variable, right? It's like if I so minimize over X, X squared plus e to the X, Then I say this one is minimized over z squared plus e to the z. A change variable, right? The function didn't change, it's just a dummy variable. Is these two optimization problems the same? Right? Are these two optimization problems the same? Exactly the same. I can pick whatever, q, alpha, beta, whatever I want. It's dummy variable, right? It's a function. The form or the structure of the function is the key. Instead of the variable I pick. I like z, you may like other variable. That doesn't matter, okay? So if you change with a little bit change of variables, you find out this is exactly this, right? So that's also value iteration, okay? If I write it down like this, that will be x1 I know is f z of u0, right? This is x1. So it's the same. So I have from v1 to v2 follow this value iteration formula. This is a pure algebraic manipulation. Sometimes it's you know everything makes sense, but you don't have intuitive way of understanding things. But I want to make sure you convince you that both intuitively or algebraically, this value iteration is not hard. You just need to know what's going on. Any questions? Now I think I have complete derivation of value iteration for you. And it works for, the value iteration works for all dynamical systems. Did I assume f is linear? Or anything, I don't impose any condition or assumption at all. So this holds for all problems, and all problems satisfy this. Okay. Now let's go back to our, oh, I forgot to mention that each time, hold on. So you do the minimization, you have a cost function, but I typically want to know the minimizer, and we call this minimizer what? This guy is called mu1 star of z equal to argmin u of this L z of u. u0 and u are the same dummy variable, okay? So plus v1 of fz of u. We call this the optimal action. We call the mu. And the action depends on the state, z. So it's called a control law. Before we also have this, right? So this, any optimization, you optimize it, you will have an argmin, right? This guy, so mu0 z star will be argmin of this as well, the whole thing. You optimize, you find the optimizer and also the optimal value. Overall, you will have mu1, mu2, mu3, mu-n star, right? If I go back to our review part, this will be our mu j plus 1, z is argmin. That's our control, optimal control action I want to pick. Of course, u belong to u of z. This is L z of u plus vj of I z of u. That's argmin. What does this mean? I want you to speak it out, okay? Not the equation. What's the meaning of mu? Let's call it star, okay? What's the mu j plus 1 z? The optimal control action you need to take if there are j plus 1 steps left and you are currently at state z. You know the difference between j and z, okay? Hopefully my pronunciation is clear enough that you know this is j, this is z, okay? J and z. It's hard. All right, you see the meaning? Okay, now let me test you a little bit. I think I tested you already. So x0, you apply the optimal control action u0 star. Suppose n steps, right? You move to x1 star, then you apply u1 star, you go to x2 star, keep going. And I can tell you that this u0 star, that's the control action, equal to mu n star of x0. Why? Because it's the optimal control action you need to take if there are n steps left and you are currently at z, which is x0. Okay, and u1 star is mu, how many steps you left? Suppose n horizon problem, okay? N minus 1 star, what? x1 star, right? Depending on your state, depending on where you are, your contraction is different. And this mu of that is a function. That means all the optimum contraction is a law, right? It's basically a function. If I say mu of n star of x0, that's a control law, right? That maps state to control action. I can tell you that if my control law is mu n star, this is function, right? Whatever state I put into, I will apply a control action. And then that's my system. If I do this, this is MPC. Okay, that's exactly MPC. I don't think I have time to go through the details, but that's exactly MPC. And you can analyze its behavior. You see, if you want to apply the n horizon optimal control, your control law keeps changing. Did you see the difference? The first one, you apply n horizon. The next one, you apply n minus 1 horizon because your horizon is shorter one time. Okay, you're given a finite time. But if I keep applying the n horizon, I didn't change the horizon size. At any given time, I think I have n horizon into the future. Okay, I keep repeating this optimal control law, then I have a MPC, model predicted control. Because once I apply this, then I forgot about U1 now. I just redo it again. So this is optimal control law. We can analyze its behavior, even analyze stability, closed loop stability under MPC controller. I think next semester I'm going to talk. Well, I don't think you can take it. I'll talk this in the more details about, hopefully everything about MPC next semester. That's enough for the review and a little bit more in-depth discussion. Let's go back to our example. As I mentioned, if you don't write code, you don't understand. Okay, let's see, this is we didn't write code before, right? So this shortest path problem, almost trivial to solve, but we need to know, or we need to derive solutions as if we are the program. Okay, we design a terminal cost, we design running cost, which is the length of its link. Then we do the value iteration. Did you remember? This graph can be really large, right? In the exam, in the homework, the last homework, you are asked to do, you forgot about homework? You need homework, I think. You will love it, I think. Because without it, you may not know what to review for the exam final. The airfare problem, that's the homework, right? Today I'm going to write a code for you as a starting point for you to solve homeworks. I never done this before, okay? Let's just write a code to solve this problem. DP. How hard the DP problem is? or the coding, a few lines of code. If you know, everything is a few lines of code. Let's try to write these few lines of code. Let's see, let's ME. Did we have a dynamics? Did we formulate this problem before as an optimal control problem? Right? That's our formulation. That's the state update equation. That's our state space, right? Running cost, terminal cost, and optimal control problem. This is running cost, terminal cost, and this, right? How do we write code? That's really important. I think let's, hold on, let's do this. It takes me some time to type in all these numbers. I'm not sure whether it's true. That's 8 by 8. Let's see, okay? 8 by 8. Let's print cost matrix. 8 by 8. It's symmetric because the link, I think, is undirected graph, okay? From one to the other versus the other from one is the same cost, all right? From this means if you stay at 0, it's 0 cost. If you from, not 0, 1, okay, let's say 1 to 2 is 4, okay? Let's look at our 1 to 2 is 4. 1 to 7 is 6. 1 to 7 is this one. All the others are -1. I just use -1 to mean big, large, infinity, whatever. Okay, I can assign this cost to be different things later on. But for now, it's just -1 means infinity in this cost matrix. All right? Hopefully you trust I think it's right. Okay, that's the cost matrix. That's the graph. Okay, now we are trying to, let's see. Hold on. Now we are trying to solve the problem. First of all, how to get started. Let's, about different people define different. I like to do the value iteration first, okay? So value iteration, define. How to do define? Define like this? No, define value iteration. Okay? The thing I need is the V function. I also need the cost matrix. And for the value iteration, I also need to know, let's say, terminal state. Okay, I need to know terminal state. So what we need is each time I need, let's say, J. Let me think. This step. Let's try to map to the math. Okay, so each given time, we need to compare a few things. What are the things we need to compare?
I think we can build a table for lookup or
Yeah. Let's okay. Let's follow my notes. Okay, let's just map the math to code. So this, for each U, you need to compare running cost per class plus the next value function cost, right? And for different U's, you need to pick the one that's the U that minimize all the possible actions, right? So I will call this J of U equal to, let's initialize it, let's say -1 or np.1's, what's the dimension? Let's do a little bit general, n equal to cost matrix. Let's directly hard code it, sorry. 8, okay? This is n. I also need the value function, which is value, let's say v next. what we are doing value iteration from Vj to Vj plus 1. Let me repeat. You give me Vj, I need to tell you what Vj plus 1 is. And also I tell you what's the optimal control action I need to take. Vnext is also whatever initialization is fine. Let's just say -1 times np dot ones n. What else I need? I also need to mu. Mu star. Mu star is -1 times np dot ones n. Okay, that's some initialization. Then I can start. For each state, just need to repeat what we did here. For all the z, you need to find a function. That means for all the possible state z, you need to compute the value and also compute the optimal mu star, right? So if you have a for loop that for, let's say, xi, that means the index for state in range n, hold on, that's fine. And for ui in range, because u also control action that I can take. In general, I don't know what I can take. Let's say just n, all the state I can possible, but some state are -1. That means impossible, right? And this is what is it? I need to compute j of ui equal to, for each state, look at this, okay? V is the minimum among these two, right? So that means for each u is running cost plus the previous, okay? So that will be a cost matrix from xi to ui, yes, right? That's my cost, okay? And plus the v function of, suppose it's also n-dimensional vector, next, right? Next is ui.
I think it's named Vnext.
No, v function.
So Vnext is this.
J plus 1 is vnext. V is the current Vj. This is Vj, I need to compute the vnext, right? If I want to do this, I need to return vnext, that's Vj, and mu star. That's my return of my value iteration. That's it. Of course, you need to make sure we need to do this. Cost matrix, if cost matrix here, ui, sorry, this guy. Xi ui is equal to -1. This infinity, I cannot do the traditional sum, right? I would just say, here, more. That would be my j of ui equal to, that's two very big number, okay? All right, that's almost like infinity. And this guy is this. I think that's it. Then I need to do, then of course. V of xi, what is it? V1, or if I look at my formula, let's look at this formula, okay? That means Vj plus 1 is Vnext. Vnext of this state equals to the mean of this, right? So that's the equal to numpy dot j. Okay, and this mu star of xi, which one? Is this one. Mu star x1 is equal to np dot argument j, and that's it. Okay, I think that's roughly.
I think there need else for if all.
Oh, okay. Okay, yes. Else. Okay, there's no bug, that doesn't mean it works. We'll continue next class, okay? Take a break. I modified the code a little bit, so before my diagonals are all 0, that means I can stay at the current state without incurring any cost. Okay, I don't like this behavior. I want to encourage them to move. So I change it to I change the diagonal to be 10. Okay, so you have to move. Otherwise, it's not like you. Otherwise, they will keep. I would like them. Let's say if you have more. Suppose you can get to the final state in 4 steps, but I gave you 10 steps. Then previous call structure, you can stay at the beginning, waste 6 steps, then move, right? But now I want to make sure you just go to there, then stay, wait for the end of the time horizon. So that's how I changed the call structure to reflect my objective. You see what I mean? Nothing is given for sure. It's just how to encode your objective into cost functions. And then this one is now it depends on the initial state. I think the terminal ones. If your terminals, I already decide the optimal control is just stay. If your terminal, your optimal control is stay, and the optimal cost is nothing because there's no running cost. You stay there. If not, in the final cost, then it's just what we wrote down just a few minutes ago. And that's our validation. Then we can start, okay? This is, I have n state, 8 states, right? 8 sites. Horizon I gave is 4. I can give more, by the way. And terminal I want to go to, in the lecture note, where we want to go. 4, right? For the index, it should be 3. Okay? And that means the terminal state is this. So I can assign a terminal cost G function, which is all infinity. This is infinity, all right? Except I would say xf dot ith type int. Okay, so except this thing. I'm not sure whether it's floating or not, but anyway, I want to use that integer to index it. So G of the terminal state is 0. Okay, then I start my value iteration. Okay, the first value iteration is I have n horizon, and every time step I have this is V of all the states, right? State is small n. And mu is also the same thing. It's mu1 of z, mu2 of z is a function. And so that's, in this case, each row is a function, right? And initially, the first row is g. V0, that's exactly the math here. V0, what? V0 is this. Okay, so that's it. Then I do value iteration, that's one line of code, that's it. I solve it. If I run it, hold on, run it. It doesn't work this way. Let's just hard code it for now. Okay, it works. Now I need to find the optimal path. I solve it. What did I solve? If I want to for print v function, and let's say print mu function. Okay. So those are the functions. Each row is one. Let's say this one. The first row is what? The 0 horizon optimal control cost, which is exactly G. So everything is infinity except 4, the fourth one, which is the 3 index, right? Index 3. And this, we don't have U0 because we start from to have some action to take at least you have one horizon, right? If you have 0 horizon, there's no control action you need to take. So this is the initial values. All right, the second lines, second rows are the optimal one horizon cost. Okay, for example, this one means if I have one time horizon, if I start from 3, this is 3, it's 2 to 3, right? The second row, third column, that's 2 to 3, the optimal cost is 5. Right? One horizon. Sorry, no. This is from 3, right? So if I have one horizon, you start from 3, A3, that's the third city, then the cost is non-trivial now. It's not infinity, it's 5. If you look at this figure, if you start from 3, yes, you can get there in one horizon. It's no longer infinite, it's 5. Okay, that means that. So anything that is not, if you're at one horizon, you still at, you already at 4, then you stay there. There's 0 cost. Then this is from 1, 2, 3, 4, 5. From A5 to A4, right? A5 to A4, the optimal cost is 2. It's like that, all right? Of course, you can say it, but you want to make sure your code can do it. Then you can arbitrarily generalize the problem to arbitrary complexity. So that's the meaning. Okay, so we have a control function, control law, and also optimal cost function. The way we started is like say, I want to have the optimal control path. Let's say we start from, either way is fine. Let's start from 1, right? Start from 1. 1 is 0, right? Start from 0, okay. Start from 0, the first, then you need to apply your optimal control law. If you look at the math, the optimal control law, right? You start from time 0, you apply the n-horizon optimal law. That means the optimal control action you need to take when you're at this state, there's n-horizon left. Okay, and then you apply it, then you go to n-1 horizon left, things like that. You apply this. So that will be, because our f is just u, our f function is just you directly control your next step, next control state, next state. So that will be mu k plus 1, x k plus 1 is mu, n-1 minus k, that's the, if you check, you can check, okay? If k is 0, that means you have n-1, that's n, right? So Python has index that's start from 0. So that means n. So you have n horizon left, then at this time you are at xk. At least xk, I think I need to use this, right, as state. So I apply this, it works. Then if I print my optimal control trajectory, what is it? Okay, 0, 1, 2, 3, what's the optimal path? 1, 2, 3, 4, that means, right? So that means 1, 2, 3, 4, this is, what is it? 7, 12. If I can go, this is also 12, right? This number is bad. But hold on. If I change this to 6, 3 to 4 to 6, let's change that, right? Let's change it. Can I do this? 1, 2, 3, 3 to 4 is this one, to 6, and 4 to 3 is this one, right? 6, isn't it? Yeah, symmetric. Okay. If I run it, let's see. 3 to 6, 3 to 4 is 6. This 4 to 3 is also 6, right? Then I don't need to rerun this. I just need to run this. And this guy, then I have different sequence now. I don't like 0, 1, 2, 3. It looks like cheating. So 0, 1, 7, 3. Why is that? 0, 1 means 1, 2, 8 is 7, right? 3. Because this guy is 6 now. The optimum path is this. It will automatically find this. I think this, I can upload this code for you, and you almost have your code base for your homework. I want to save your time. Any questions? No questions. Okay. Let's try to learn the LQR. And it's very important, almost one topic. It's the most important topic for after a common filter. All we want to do is LQR, but it's similar to common filter. I spend a lot of time do the background, then common filter become just linear Gaussian estimation, minimum mean square. If you know all these foundations, common filter, you can derive very easily. And similarly, in LQR, we are just trying to know a special case of DP. Nothing changes, all right? It's just the F function is linear, and F function is linear, and also cos function has a special structure, so you have a analytical form for the value iteration, okay? If I want to repeat, or I have to add to this point, I need more space. Do this. Where is it? Okay. Here. Okay. Hold on. Insert page. Okay, here. So based on our coding, you can see that for that case, I need to enumerate A1. So it's 1, 2, all the way to 8 numbers, right? So I need to do a for loop to enumerate all this, right? But if I have, let's say I have a line. This is discrete. This is small cities, right? So if I have a line, let's say my state space is R. Let's say not R. My state space is temperature, Shenzhen temperature. Let's say today is pretty cold. 0 to 35. That's not true. 0 to 40. Okay? Suppose that's my state space. Suppose, okay? It's continuous. How many states I need to enumerate? Infinite. Typically, you would do what? This is 0. This is 40. You would do some tiny grading. This is called grading, right? Suppose I want to make sure it's pretty accurate. I'm grading with size, with grid size 100, right? Then I need to do for loop for 100 states values, right? From 0 to 0.4 and so on and so forth, okay? So that's case, but this is 1D case. But if my state is Shenzhen Guangzhou temperature, maybe I can say this is x1 and x2, two-dimensional, right? x1 belong to 0 to 40. x2 also belong to 0 to 40. Then I need to do gradings, right? How many grids I need? Equal to 100 squared, which is 10,000. I need to do for loops in 10,000. Although I can solve, did I say that I can solve everything using DP or optimal control? That's true, all right? The problem is that theoretically I can write everything in terms of optimal control problem, but when the state dimension is higher, complexity grows exponentially. Suppose I have x1, x2, x10. Suppose I have 10-dimensional, maybe a very simple aircraft or a simple dynamic, robot dynamic model. Then number of grids, points. I need to do for loop is 10 to the 10. 100 to the 10, sorry. 100 to the 10. We cannot do it. All right, I think current computer can do maybe up to 5 or 6. But you still need to do it in a smart way. And this can only be solved offline. Okay, so you see the catch. It's not, of course, everything can be formatted this way, but we cannot solve it. Unless so this is called, so the complexity, I would say complexity grows exponentially. Okay, this is called commercial, and this is a famous term called, this is called curse of dimensionality. You have to know. All the optimal control problem, reinforcement learning, Markov decision process, learning, they suffer from the curse of dimensionality problem just like this. Okay, you cannot do high dimensional things because they suffer from 维度灾难, okay, curse of dimensionality. Okay, unless exceptions. So what we can do is, of course, discrete problem that you may have 10,000 or 20,000, okay, computer can handle it, just do for loops and code, write your code smartly. You should be able to do it. But in general, if you have high dimensional state space, it's hard. Exception is LQR. That's an exception. It's not a standalone theory. I'll say this exception to curse of dimensionality because no need to do grading. We have analytical form for value function and mu j star. Okay, the reason we want to do for loops is that we need to enumerate all the possible state and tells you or compute the optimal cost to go and optimal control action I need to take. The exception means I don't need to do it. I can derive a formula for it, so I don't have to do for loops. Okay, that's LQR, and we're going to use 10 minutes to cover it. Once you know DP, that's just the exercise. Okay, I hope that logic is clean now. Let's start our introduction to, LQR, linear quadratic regulator. Very, very important nowadays. When I was a student, nobody used it. Now, because the computer is faster and the robotics people like to use it, and it's become a standalone thing that everyone have to know, especially people in robotics. Okay, and first of all, I want to emphasize LQR is the same as Kalman filter. The formula are the same. The optimal feedback gain is Kalman gain. It's a dual problem. Okay, it's like a controllability versus observability is dual, and LQR is the dual to Kalman filtering. Okay, we wouldn't cover that, but the formulation is like the following. Before we have reviewed optimal control problems, right? So before we have general optimal control problem like this. Now the difference is what? The F becomes AX plus BU that we focus on. Simple, right? Deterministic and also linear in both control and the state. And before the cost function is arbitrary. This is my running cost now. It's a quadratic function of state and control. Any questions? What does this mean? So this is running cost and also terminal cost. This is my g of xn. So IQR is just a special case of nonlinear optimal control, of course. So this is g of terminal cost. Terminal cost is a function of, it's quadratic function of the terminal state. Why we like quadratic function? Because we can solve analytical form for it. It's like a least square. Okay, so it's no y. Okay, it's just this way can capture our objective to a certain extent, and also the benefit is that we can have analytical form for the optimal solution. Okay, so So quadratic function, I think I can just briefly mention it again. So this is z transpose p of z is a function from Rn to R. If you give me a state, I give you a number. That number is a so-called quadratic cost terms. So if I choose my p to be identity, then this is nothing but the norm of the z. Okay? If I pick it, this is just norm. Why I want to minimize the norm? Because I don't want it to be large. Okay. If I pick it to be a diagonal, but one coordinate is bigger or smaller than the other, then I have the form is like this. If you just multiply things out, so z is z1, z2, right? If z transpose pz will be just this. So what does this cost means or indicate? You penalize x2 more twice as large as z1. So the second coordinate is more important. I want it to be small. Okay? So that's all it means. Will allow you to, in general, it could be just anything that is positive, semi-definite. It will be valid for a quadratic cost function. Okay, so I want to. So the goal is, you can see from this LQR, the goal is to use small control action or effort to make your state converge to 0. That's why it's called a regulator. And the state, in general, as we mentioned before, we want them to go to 0. That 0 is a quote-unquote 0, means your desired position. Your 60 miles per hour. Your 25 degrees of degrees. Okay, so that's whatever desired value you want. You call that the origin, then x is deviation from that. Okay. Any questions? We have the same formulation, is just specialized in linear system and quadratic cost. That's why it's called linear quadratic regulator. Okay. To solve it, what we do is dp. What is dp? Initially, what we have is terminal cost. What is the terminal cost? G of xn, right? G of z. Z is a dummy variable. Okay, it's representing the function. So what does this mean? If you have 0 horizon, that means you don't have any time to live. Then you're at z, that's your cost. Okay, terminal cost. And now we need to do value iteration, right? Before we just do value iteration through for loops, but now for linear quadratic regulator, we somehow can find the optimal solution analytically, because it's just nothing but a minimization problem, and in this case we have an analytical solution just similar to least square, I think, right? And I make a conjecture. It's not I make a conjecture. Let's assume, first of all, the J horizon problem is of this form. What is this form? A quadratic function. Okay, suppose my J horizon cost function is a quadratic function. It holds, for now we know, for J equal to 0 already. Right? Let's assume it holds for J, and we want to prove j plus 1 is also a quadratic function. Okay, so now let's derive it. So let's say vj plus 1z is of this form. So yeah, what does this form mean? What is it called? Is this something special to LQR? Is this DP? Similar, how similar? The same, right? This is called value iteration. Okay? This is value iteration, exactly the formula I gave you before. Because now L is what? L is the quadratic in Z, quadratic in U. This is running cost, right? As I mentioned before, this is my L. L is xk transpose qxk plus u transpose ru. Okay, that's my quadratic cost. I penalize both state and control. Okay, I plug in this here. Let me zoom in. And the Vj of next step. Next step is what? F is a linear function, right? So it's az plus bu times p of j. So that's my assumption. Vj is a quadratic function. I assume, at least from 0, we can do this, right? And plug in this. Then I can group terms. Hopefully, I think you can verify when at home. And group terms, I can write it like this. Okay, it's a quadratic function in both state z and u, control u. And what we want to optimize? We want to optimize with respect to u. So I write it in terms of a quadratic function in terms of u. Z is some kind of a parameter or constant in this case because we only optimize over u. We want to pick the best u such that this function is minimized. Okay, so this fxu is just hu is just this function. In this case, what we should do is this. I think this is in essence is the same as least square now, right? What you need to do is take derivative with respect to u. Okay, this function h is from Rm to R. It's a quadratic function. It's you can write it like u transpose a quadratic function. That's a capital Ru plus something, a linear function of u. So anyway, that's this. You take derivative, it will become this, and let it equal to 0. You can solve for u, right? That's your take derivative. And you solve it, that means you invert it. Overall, you have this. So that means the optimal control action at this time is some matrix, a lot of matrix multiplied together, times z. And I will call this guy k of j plus 1. If you look at nature, it is a linear function of the state. Okay, it's a linear function of z. That's my solution. When I solve this optimization problem, it's a linear function of the state z, then that's my solution. Okay, you can go back to check. And this is, I define it as a gain. This is a Kalman gain. Okay, this is a Kalman gain. It's like Kalman filter gain. It's the same thing. This is the covariance inverse, right? You remember? Very interesting. Okay. Any questions? That's your optimal one. Then I plug in this guy, right? So this is my optimal u. What's my optimal cost? I need to plug in my optimal u to have my optimal cost. The optimal control, I plug in this u star, becomes this. I mean, after some kind of manipulation of those symbols, I find it out. this is nothing but of this form. Yuntian, is this a quadratic function?
Yes.
Of what?
Of V.
Okay, although it looks complicated. I'm going to ask you, is this a quadratic function of z? Yes, it's of the form this. And I can call this animal, this very complicated animal, my pj plus 1. Okay, that's my pj plus 1. That relate to pj, relate to ab, and also my cost function structure. And so this is, now I validated my proof, right? So if I start from a quadratic function, value function, next time I will also be quadratic function. And next time I will also be quadratic function. It just, this p changes, right? How does that p change over time? From this recursion formula, this is called Ricciardi recursion formula, okay? It's not a Ricciardi equation yet, it's a Ricciardi recursion. Ricciardi equation or Ricciardi recursion is very famous term in optimal control and robotics as well. And this update formula should be the same as common filter. The covariance gain, covariance matrix update equation is the same. Okay, if you pick your notation, and they are the same. It's just like AB is observable, almost like, right? Controllable and observability, things like that. AB observable is A transpose, B transpose, AC observable means A transpose, C transpose controllable, things like that. All right. So the optimal control action you need to take is just of this formula. It's a gain. I think it's there should be a negative sign here. A gain times the state. So its optimal control action is linear, and this gain can be computed. Okay, and this is, so the meaning of this is the optimal control law you need to take once there are n minus k steps left and you're at xk. All right, and this is the optimal gain you need to apply. And to compute this, you need to compute the Ricciardi recursion formula, which is J. You need to Pj. Once you compute Pj, you can define K. Once you define K, you know what optimal action you need to take. That's a summary. I wouldn't want to go over it in details, but how to solve it, by the way, you just do the Ricciardi recursion. You start from P0, okay? Whatever P0 is fine. Terminal cost, that's your terminal cost function, okay? P0 is nothing but Qn. You can pick arbitrary positive semi-identity matrices, and then you do the recursion. You have P0, you have P1, you have P2, all the way to Pn, okay? What does Pn means? Why we care about P? Because we care about V. Okay? Vj of Z. I mean, value iteration, right? We do the shortest path problem. We do value iteration. All we want to do is compute this guy. Right? Now, in this case, this guy is nothing but J transpose P of Z of J. It has a parameterization in finite state, a finite dimension. I don't need to enumerate all the Z. I just need to find a matrix. Okay? So once I find this, I know Vj, and I also know corresponding mu of J star, which is a common gain related to it. All right? That's it. So our QR controller is just you. At any given time, once you find this, you find a K, and then you just move your system along the optimal path, right? In the infinite horizon case, I have 15 minutes, okay. Infinite horizon case, it can be proved that AB is controllable, AG is observable, where Q is G transpose G, okay? You could decouple G. And then the value iteration converges. And once it converges, the optimal gain it's stable. Your system is stable, exponentially stable. And this satisfies the algebraic, this is called Riccati algebraic Riccati equation, right? So when the update doesn't give any changes, converges, the value function converges. Okay, then the gain converges. Well, you don't need to have so many time varying gain. You have a stationary gain to apply. That's optimal gain. Okay, let's look at the code again. This is the RQR problem. We have this AB matrix. B is two-dimensional now. Before we did our pole placement, typically we can do pole placement for one-dimensional U by hand, and the high dimension I want you to use place function in MATLAB or in Python. In this case, that's a state, so I can plot without any control. Suppose I don't know how to control the open loop system. Is 10 to the 13 is unstable, right? The diverse. The system is open loop unstable. I have to design my controller carefully. If this open loop stable, then I can apply zero control. It's still stable. I don't need to do anything. It's good, but I can do things to improve its performance. Now we can design our LQR controller. Design LQR controller, import this linear algebra package. Then let's now use zeros. The terminal, this is a weighting matrix. So that means this identity means I weight all the state the same. Okay, and R is the also identity. The control weighting is. I'm just trying this first. Okay. For testing purpose, let's first verify Riccati recursion formula. And so if I run this, by the way, it's just one for loop. This long equation is, I think it's just, I type it on this Riccati recursion. Okay. Q, A transpose P, A minus A transpose P, B are whatever inverse. So Q, A transpose P, minus A transpose P, B inverse of this is exactly typing down the Riccati recursion formula. And what we are computing is the optimal value function. Okay? The optimal value function is represented by P now. Okay? It's a quadratic function. So I do the formula for 200 steps. If I plot these 200 steps, they are the same. It's 199 or 198. The last two matrices are the same. Actually, I don't need 200. I think I need, it will be converted pretty quick. 20 is fine. But I don't have it anymore. 19. Okay, it's already converged. It's exponential convergence very fast. I think 10 steps or 15 steps will be converged pretty fast. Why it converge?
We penalize if it's not.
It's like, okay, think about this. It's a value function, the optimal cost, right? So if the system is controllable, that means you can drive it to zero. Of course, you cannot drive to zero next step. Maybe you given 4 steps, or let's say 10 steps. You already can make it very, very close to zero. But if I give one more step to you, the cost doesn't change any much, right? You cannot reduce the cost further. So once I give enough time horizon, you are able to do this, right? So then that somehow after the horizon size is big enough, then it doesn't change anymore. Okay. Now let's see, let's check. This is K star. This already converts. I just use the K star. Look at the K star, the eigenvalues is, wow, where's the eigenvalue? It's hard to see. These are the eigenvalues. I think they're all close to 0. Oh, sorry, this is all stable at least. Okay, I print too many things. I don't need to print these two anymore. Okay, these are the arrays. These are, the first array is the eigenvalues. Okay, those are eigenvectors. Before it's an open loop unstable, but all I want to make sure is that the converse one is stable. Okay, and then I can keep applying this control, this stationary control action. Now let's check the performance. How do I check the performance? I need to simulate the system under this optimal control. How do we do it? We start from some initial state. The 1, 2, 3 is the same initial state as we did before for the open loop one. But now instead of using 0 control, now I use optimal control. How do I compute optimal control? In this case, I just keep using K star, sorry. So I didn't do the time varying. This is KJ, right? It's K, first you need to apply K20, then you need to do K19, K8. The performance will be same or similar. UK is K star again times this. And I also compute the norm of U, and then I evolve my system using this U. Okay, and then I plot it. Before it diverges, now it converges. So this x1, x2, x3, this is the U norm. You see, U also converts to 0, and that's how it works. Now let's jump to the next one. If I change it, let's say I change my cost function. Okay, before I have identity, right? Now I make my Q 100. The first element is 100. What does this mean?
It needs to be more stable. Stabilize faster, much faster.
Okay, so that means x1, I want to penalize x1. I want it to be smaller, right? I think it's 100%, 100 times more important than other state. I changed my U, because I don't want to rewrite this. I just have my own LQR. By the way, if you call DLQR in MATLAB, the Python, I didn't find this. I coded it by myself. It's just this. Then this is, let's see, I find the optimal value function P and gain K. Then I have, this is new, right? Before I called it X. This is X. And this, I change the cost, and that becomes new. I compute them together. The red one is the previous one, I think. Red one is the X. The blue one is the new, okay? What did I care more before? I care more X1. The blue one becomes dramatically smaller, okay? But there's no free lunch. X2 becomes bigger, right? This is blue is a new one, right? X2 is bigger than before because you care more about X1 now, okay? And the control action is also bigger, all right? And you can play with it. If I care this guy and this guy, X1, X2, both are more important. I can see that doesn't work well that much. X2 is more, it can be handled. Where is it? Okay, X2 is smaller than before, and you sacrifice a little bit. There's no kind of strict constraint. If you add more constraint that you wouldn't be able to derive the formula analytically, then you have to use MPC. You have to do it on the runtime. I can penalize, let's say this is 1, this is 1. I can penalize my control action more, let's say 100 times more. So I don't want to waste my control energy. And you can see that the case, which one has bigger control action or energy? The blue or red? The red one, right? The total energy is the one underneath the curve. Okay? That's the total energy. The energy underneath the curve, I think the blue one is smaller. That's the new one is smaller. If I take more extreme, it doesn't work. It's almost like I don't know why it doesn't work. No, it doesn't behave like the way I want. It's almost the best I can do. Maybe I can make it more. The other one is only 30 steps. I don't think we can see that much difference within 30 steps. That's why I want to change. Anyway, I think you can play with it. Okay, I don't think we have time for quiz today. Do we? 4 minutes. I have a really hard quiz for you, but okay, that's almost the end of LQR and the end of everything for this semester. Next time we're going to review. 怎么了？你还想多学点儿？我本来想讲一下 MPC 的哈，但我感觉一个 lecture 讲可以大概过一小点，可能意义也不大，我还不如把我们已学，其实你已经接触到很多了，稍微看点资料就差不多了，我们可以就是把该学的东西学的稍微深入扎实一点就更好吧。那下节课我们会比较深入的 review 一下，好吧？我们这个学期包括从开始，好吧？然后呢，我希望你们还是事先做一点点复习，好吧？要不然你都忘了我搁这讲呢，这个效果会比较不太好。所以最近1-2天，在周3之前呢，你稍微做点复习，就会好一些。